Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. Cosmos. The word itself is like a soft whisper in the dark of night, inviting us to look up and wonder. Born from ancient Greek, it means order or ornament, the opposite of chaos, the adornment of the night sky. For as long as humans have had language, we have given a name to the grand scheme of everything. We have always stood under the starry vault, hearts beating with curiosity, minds aching to understand what it all means. In a silent desert or on a grassy hill, our ancestors gazed at the stars with awe. Tiny lights flickering in the vast darkness became stories, became gods and guides. Under that cosmic canopy, they felt small yet connected to something immense. They sensed in those pinpoints of light a pattern, a rhythm, seasons changing, moons waxing and waning, a cosmos moving with purpose. To say cosmos is to imply the universe is not a random scattering of matter, but a harmonious whole. Beyond the chaos of daily life lies a greater order we can barely fathom. When we whisper the word, we summon an ancient feeling, the awe of knowing we are part of a mysterious, breathing entirety. The cosmos has always beckoned us. It humbles us with its scale and age, yet it also comforts us with the idea that we belong to it. We have wondered if the twinkling lights had messages for us, if the sky was a story written in stars. Generation after generation, we pass down myths and measurements, trying to bring the heavens into human understanding. Through wonder and imagination, we wove ourselves into the fabric of the cosmos. Even now, in an age of bright cities and glowing screens, that old impulse remains. Go somewhere dark and clear and look up. The same Milky Way that dazed our ancestors arches overhead. In that band of light, millions of distant suns blurred together, we find both our history and our destiny. We feel the tug of an ancient question with each breath under the stars. What is all this? What does it mean that we live in a cosmos so vast and beautiful? From the earliest times, cosmos has meant more than just the physical universe. It carries a sense of profound order and connection. To reflect on the cosmos is to step beyond oneself, to see life on Earth as part of a larger story. It is to realize that the atoms in our bodies were born in stars, that our existence is tied to cosmic events beyond memory. It is to feel both tiny and tremendous, a fleeting moment and an integral part of eternity. So let us meditate on that word and all it entails. Let us journey outward and backward, upward and inward. In this story of the cosmos, we will travel from ancient myths to modern science. We will seek patterns in the sky that guided our ancestors and follow the light of distant galaxies that reveal our cosmic origins. We will ponder forces unseen and marvel at galaxies strung like jewels on invisible threads. Through it all, we hold on to that childlike wonder that first taught us to say cosmos with reverence. Our voyage begins where it must, in the tales and dreams of those who first looked up and tried to understand. The cosmos has always been our mirror and our muse. In its vastness, we have found grand myths of creation, of gods and monsters, of order emerging from chaos. To truly know the cosmos, we start with the ancient stories written not on paper, but across the sky itself. The ancient cosmos. Before science, there were stories. In the cradle of civilization, human beings looked to the sky and saw a grand drama unfolding above. The cycle of night and day, the march of seasons, the wandering of planets among the stars. All these celestial motions cried out for explanation. And so our ancestors gave the cosmos a face, a script, a meaning. The ancient heavens became a mirror of life on Earth, a canvas on which they painted their hopes and fears. In ancient Egypt, each sunrise was not just a new day, but a victory of order over darkness. The sun was the god Ra, sailing across the sky in his brilliant boat. Every morning he was reborn in the east, bringing light and life. Every evening he descended into the underworld, battling forces of chaos to ensure the sun would rise again. To the Egyptians, the cosmos was upheld by these divine cycles. Ra's daily journey affirmed the rhythm of life, death, and renewal. The Nile would flood and recede, crops would grow and be harvested, just as surely as the sun would set and rise. Their myths gave cosmic meaning to earthly patterns, reassuring them that the universe was orderly and life-sustaining as long as the gods maintained balance. Far to the north, under Greek skies, people also sought cosmic order through myth. They imagined the night as a storybook opened overhead. Constellations were characters, a great hunter forever chasing a bull across the heavens, a hero carrying the weight of the sky on his shoulders, a queen enthroned among the stars. The Greeks looked up and saw legends. Orion with his shining belt of 3 stars, majestic and bold, the Great Bear lumbering around the North Pole, Andromeda chained to her stellar rock. Each constellation marked a tale of love or bravery or caution, a lesson twinkling from the firmament. Above all reigned Zeus, king of the gods, whose authority extended over both the sky and human affairs. The moving planets, the wanderers, were given names and personalities: fiery Ares, Mars; bright Aphrodite, Venus. By telling these tales, the Greeks found patterns in the stars, a cosmic order reflecting their own virtues and vices. The movement of the heavens hinted at divine plans. If Mars appeared red and bright, was Ares signaling war? If Venus rose in the evening, did Aphrodite bless lovers? In this ancient cosmos, the boundary between heaven and earth was thin, each influencing the other. Across the ocean in other lands, countless cultures wove their own cosmic tapestries. In old China, the night sky was envisioned as a celestial empire mirroring the earthly one. The emperor was said to be the son of heaven, and the stars were arranged into palaces and provinces. The Chinese sky was divided into constellations, forming a meticulous heavenly bureaucracy. A comet streaking through the sky might be interpreted as a wayward official or a portent of change in the kingdom. An eclipse was not just an astronomical event, but a dragon devouring the sun or moon, a sign that the harmony of the cosmos had been disrupted. To restore balance, people gathered to beat drums and gongs, scaring the dragon away. When the sun returned, it reaffirmed the cosmic order and the emperor's mandate. Through such rituals and myths, the ancient Chinese made sense of celestial motions as reflections of moral and political order on Earth. In the Indian subcontinent, sages imagined a layered cosmos teeming with gods and avatars. The sky was the abode of deities riding the clouds. The sun was Surya, a radiant god who drove his chariot across the heavens, pulled by 7 horses, the colors of sunlight. The moon was Chandra, gentle and cool, gliding through the night. The planets were also gods, each with personality and power, collectively called the Navagraha. Indian cosmology spoke of a universe born from a cosmic egg, of endless cycles of creation and dissolution, measured in kalpas, lasting billions of years, staggering spans of time encoded in myth. Yet these huge cycles tied into everyday life. The positions of planets could influence a person's destiny, the timing of rituals, the fortunes of kings. By observing the heavens, ancient Indians felt they could glimpse the divine rhythm that underpins reality, aligning their lives to the dance of the cosmos. No matter where on Earth, early peoples found ways to map the sky onto their own experience. The Babylonians meticulously tracked the movements of planets and stars and wove them into their myths of gods like Ishtar, Venus, and Marduk, Jupiter. They recorded eclipses and believed in cosmic omens, that a falling star could foretell the fall of a king. The Maya of Central America built observatories to follow the sun and Venus, timing agriculture and ceremonies to celestial cycles. For them, the cosmos was a ceaseless wheel of time, with each era ruled by different gods. Indigenous peoples of North America saw constellations as great hunters and animals, integrating the sky into storytelling and navigation. Every culture found its own cosmic North Star by which to guide human life. These ancient cosmologies differed in detail, but they shared a purpose: to make the vast, unknowable sky intimate and meaningful. By projecting stories onto the stars, our ancestors found comfort and guidance. The cosmos became a grand clock and calendar, its motions providing a sense of predictability in an uncertain world. The rising of Sirius just before dawn signaled the Nile's flood, and thus renewal, to the Egyptians. The appearance of the Pleiades in spring told Greek sailors that sailing season had arrived. The heavens and earth were interwoven in a tapestry of sign and story. Most importantly, the ancient myths gave people a sense of belonging in a huge universe. If the heavens were populated by gods and heroes, then human life was part of that divine drama. Nothing was random. The cosmos had intention, personality, narrative. A shooting star could be a departing soul. The Milky Way could be the spilled milk of a goddess or the bridge to the afterlife. By aligning with these cosmic stories, performing rituals at solstices, building temples to face sunrise, tracing the planet's paths, ancient humans felt they were participants in the cosmos, not mere spectators. In those early nights under open skies, the cosmos was both guide and canvas. People drew connections between the circling stars and the cycles of their own lives. Birth, death, love, conflict, harvest and drought, all found reflection in the movements above. The myths may not have been scientifically accurate, but they were true in a deeper sense. They captured the emotional truth of being human in a vast and mysterious universe. They helped us navigate not just by land or sea, but through the uncharted waters of existence. Thus, the ancient cosmos was a place of narrative and meaning. It was alive with motion and intention. Every sunrise was a story, every eclipse a warning or wonder, every constellation a reminder that we are part of something greater. With these stories, humanity's long conversation with the stars began. Over millennia, those conversations led to patterns noted, calculations made, and the first whispers of a new approach to understanding the cosmos. Myth would eventually inspire measurement, and storytelling would lead to science. As our methods changed, the goal remained the same: to find our place in the grand order of the cosmos, and to ensure that the cosmos made sense. The birth of the modern cosmos. For thousands of years, the Earth sat proudly at the center of the known universe in human imagination. It seemed obvious. The ground beneath us felt still and solid, while the heavens whirled around. The sun rose in the east, journeyed overhead, and set in the west, surely circling us. The stars rotated nightly around the North Star, as if painted on the inside of a celestial dome with Earth at its core. This geocentric cosmos, codified by philosophers like Aristotle and Ptolemy, was cozy and reassuring. Humanity lived at the heart of creation, the focal point of God's plan or nature's design. Above, the crystal spheres turned in orderly concentric circles, carrying the sun, moon, planets, and stars in divine choreography. In this model, the cosmos was finite, well-ordered, and centered on us. But whispers of a different truth had long existed. As early as ancient Greece, a few bold thinkers, like Aristarchus, suggested that the Earth might move around the sun. This idea was largely dismissed or forgotten for centuries. It simply felt wrong. How could Earth be moving? We felt no incessant wind from such motion, no constant shaking. And if Earth swung around the sun, where was the parallax in the stars? The tiny shift in star positions that such motion should produce? None could be seen with the naked eye. So the geocentric view held sway through antiquity and the Middle Ages. Then, in the 16th century, A Polish astronomer named Nicholas Copernicus quietly revolutionized our view of the cosmos. He proposed a bold simplification. Suppose the Sun is at the center, and the Earth is just another planet circling it. In one stroke, the cosmic order could be explained more elegantly. The retrograde loops of Mars in the sky, the cycles of Venus, all made sense if Earth was moving too. Copernicus published his heliocentric theory in 1543, carefully dedicating it to the Pope and couching it as a mathematical convenience. Yet the implication was clear. Our planet was not the pivot of creation. It was a radical leap, met with skepticism or silence by most contemporaries. After all, it upended common sense and challenged religious doctrine. But the seed of the modern cosmos was planted. It would take brave observers and thinkers to make that seed sprout. Early in the 17th century, Galileo Galilei in Italy heard of a new invention, the telescope. He crafted his own and pointed it at the night sky, becoming the first human to see certain wonders. Through Galileo's telescope, the moon revealed mountains and craters, not the perfect heavenly orb philosophers imagined. Jupiter appeared as a tiny disk, accompanied by 4 points of light that moved, Jupiter's moons, orbiting not Earth but Jupiter itself. It was a celestial ballet defying geocentric dogma. Here were objects clearly circling a world other than our own. Galileo also observed Venus showing phases like the moon, a behavior only possible if Venus circled the Sun, not Earth. Star clusters in the Milky Way resolved into countless faint stars, suggesting the cosmos was far larger and richer than assumed. With each observation, Galileo dealt blow after blow to the Earth-centered model. He wrote of his findings, championing the Copernican sun-centered system. This earned him admiration among some and condemnation from others. The idea that Earth moved was still too great a heresy for many. Galileo famously faced the Roman Inquisition and was forced to recant. But the truth was out. Our world was not the fixed center. Earth was a planet in the heavens, one among several. With the heliocentric model gaining evidence, the cosmic stage expanded. Johannes Kepler refined the picture by discovering that planets travel in ellipses, not perfect circles, and speed up and slow down in their orbits according to precise laws. It was as if the cosmos had its own music, and Kepler had begun to hear its rhythm in the data. Shortly after, Isaac Newton in England provided the masterstroke. He formulated the law of universal gravitation, showing that the same force pulling an apple to the ground keeps the moon circling Earth and Earth circling the sun. In Newton's new universe, the celestial and terrestrial were unified. The heavens were not held up by crystal spheres or angelic powers, but by gravity, an invisible thread binding planets to stars. Suddenly, the cosmos became a mechanistic marvel, a grand clockwork governed by laws that could be understood and even predicted by humans. The music of the spheres was transcribed into mathematics. The modern scientific cosmos was being born, and in it, Earth was merely one cog in a vast machine. As the centuries turned, our understanding leapt forward. By the 19th century, astronomers realized the sun itself was not the center of all creation, but rather the center of a local family of planets. The stars, once thought to be distant lanterns or holes in the firmament, were confirmed to be other suns scattered across unimaginable distances. The night sky, which to the ancients was a fixed dome, became an ocean of stars in 3 dimensions. We measured the first distances to stars and found them stupefyingly far. The nearest, Alpha Centauri, is over 4 light-years away, 40 trillion kilometers. The absence of observed parallax now made sense. The stars were vastly farther than imagined in Aristotle's time, so their parallax was tiny. Our sun was thus not the center of all stars, but just one star drifting in a great starry city. That starry city is the Milky Way galaxy, a broad band of light wrapping the sky. In the early 20th century, astronomers pieced together that the Milky Way was an immense disk of hundreds of billions of stars. Our Sun lay not at the center of this disk, but off to the side in a spiral arm, a suburban star in the galaxy's outskirts. We had been demoted once again from center of the universe to mere resident of one galaxy among possibly many. Yet even then, many believed the Milky Way was the entirety of the universe, an island universe surrounded by a void. Reality had another plot twist in store. In 1920, astronomers Shapley and Curtis engaged in the great debate over the scale of the universe, arguing whether spiral nebulae, like Andromeda, were part of the Milky Way or distant galaxies of their own. This question was settled in the mid-1920s when Edwin Hubble, using the giant Mount Wilson telescope, observed stars in the Andromeda Nebula. He identified particular stars called Cepheid variables, whose blinking rhythm allowed him to calculate their distance. The result was staggering. Andromeda was far outside our Milky Way, a galaxy in its own right. In one announcement, Hubble shattered the confines of our known cosmos. The universe was vastly larger than we had imagined. The Milky Way was but one galaxy among billions spread throughout space. As if that weren't enough, Hubble soon discovered that these galaxies are flying apart from each other. Space itself is stretching. The spectra of distant galaxies were shifted toward the red, like the lowered pitch of a receding siren, indicating they were rushing away. The farther the galaxy, the faster it fled. It was as though the cosmic fabric were inflating, carrying galaxies apart like driftwood on a rising tide. The implication was profound. If you rewind this expansion, there was a time when everything was closer together, perhaps a moment when the entire universe was a single point. The static, eternal cosmos of old gave way to a cosmos with a dynamic history, a beginning, what we now call the Big Bang, and perhaps an end. Thus, in just a few centuries, our cosmic understanding transformed utterly. We went from a cozy Earth-centered bowl of stars to an immense, law-governed expanse where Earth is a moving planet, the Sun a modest star, the Milky Way one galaxy among a multitude, and the universe itself expanding and evolving. Each step was a blow to human vanity, but a boon to human knowledge. With each step, the cosmos grew grander and more mysterious, yet also more knowable through science. The modern cosmos was not built in a day. It emerged gradually as old theories shattered and new discoveries took their place. It required curiosity, courage, and the willingness to accept that our intuitions can be wrong, that reality may be far stranger and more magnificent than our ancestors ever dreamed. By embracing a sun-centered system, by mapping the Milky Way, by discovering galaxies beyond our own, humanity experienced a kind of cosmic rebirth. We shed ancient illusions and stepped into a wider universe, guided by observation and reason. And as the scale of the cosmos expanded, so did our sense of wonder. The night sky, once a fixed storybook of constellations, became an endless frontier. We now knew that when we gaze at the Milky Way, we peer into the heart of our galaxy, and when we spot the faint smudge of Andromeda, we behold a sister galaxy 2.5 million light-years away. The light entering our eyes left that galaxy before our species existed. The modern cosmos is vast, full of galaxies drifting in the darkness, all governed by the same natural laws. This was a cosmos that could be analyzed with telescopes and equations, but it still evoked awe. In fact, the more we discovered, the more profound and humbling the mystery became. Having found our true place, not the center, but part of a cosmic community of worlds, we were ready to explore what this newfound universe looked like. With minds freed from the confines of geocentrism, and with ever more powerful tools, we set out to observe the cosmos in all its glory. The next step of our journey would be to truly behold the universe with new eyes, to collect the ancient light of stars and galaxies, and from it, read the story of time itself. The observable cosmos. Armed with newfound knowledge and powerful eyes, humanity set out to truly see the cosmos. What had been mysterious points of light became tangible suns and galaxies through the lens of the telescope. Our curiosity, once limited by human sight, now leapt forward with each improvement in our instruments. The cosmos opened like a book under a magnifying glass, revealing detail upon detail written in light. We learned a startling fact. To observe the universe is to look back in time, for light takes time to travel. Consider the starlight reaching us tonight. The nearest star beyond our sun, Proxima Centauri, lies 4.24 light-years away. The light hitting our eyes from that star left it over 4 years ago, crossing trillions of kilometers of space before gently landing on our retina. We see Proxima Centauri not as it is now, but as it was 4 years in the past. And that's our nearest neighbor. Sirius, the brightest nighttime star, shines 8.6 light-years away. We see it as it was about when the last decade began. The North Star, Polaris, is 433 light-years distant, so the light guiding sailors tonight set off around the time Galileo first pointed a telescope skyward. With every step up in distance, we peer further back in time. The Andromeda Galaxy, faintly visible as a smudge, is over 2 million light-years away. When its light began its journey, early hominins on Earth were chipping stone tools. This realization transformed the night sky into a kind of cosmic history book. Telescopes became our time machines, collecting ancient photons that have been traveling for eons. By capturing this light and studying it, we decode stories from long ago and far away. The color and brightness of a star's light tells us its composition and temperature. The Doppler shift of a galaxy's light reveals its motion through space. When we see the glittering band of the Milky Way, we now understand it as the combined glow of billions of stars, many whose light has traveled tens of thousands of years to reach us. To look out is to look back. As telescopes grew in size and sophistication, the depths of the observable cosmos unfolded. In the 19th century, astronomers with new refractors and reflectors saw that some fuzzy patches of light, nebulae, had spiral shapes. They suspected these might be island universes, galaxies outside our own, later confirmed by Hubble. Each advance in observational power was like opening a new window in our cosmic house, offering a view further into space, and thus further into the past. In the 20th century, we launched telescopes above the blurring veil of Earth's atmosphere. The Hubble Space Telescope, deployed in 1990, proved transformative. Free from atmospheric distortion, Hubble could stare deeper into space than any instrument before. In 1995, astronomers did a daring experiment. They pointed Hubble at a seemingly empty, dark patch of sky near the Big Dipper, where no known stars or galaxies were visible, a speck of sky no bigger than a grain of sand held at arm's length. They let Hubble's camera soak in light for 10 straight days. What came back was a revelation. The now famous Hubble Deep Field image. Far from empty, that little patch of darkness was overflowing with nearly 3,000 galaxies, of all shapes, sizes, and colors, each a swarm of billions of stars. Some were relatively nearby, but many were incredibly distant, their light having traveled for billions of years. In those dim smudges, Hubble had captured galaxies as they were when the universe was young, cosmic baby pictures, just a few billion years after the Big Bang. That single image was like a core sample of the universe, drilling down through cosmic time. It showed a universe teeming with galaxies, even in a tiny, unremarkable bit of sky. Later, Hubble gazed even longer and deeper, producing the ultra-deep field in 2004, and then the extreme deep field in 2012, revealing galaxies more than 13 billion years in the past, when the first galaxies were just emerging. In the Hubble Ultra Deep Field, almost every point of light is an entire galaxy. Some are seen as they were only 400–800 million years after the Big Bang, full of newborn stars. By looking far away, we looked back to a time when the universe was young. Every telescope, whether a backyard amateur's or a great observatory in space, is fundamentally a light collector. It gathers the sparse, ancient photons that rain down on us, focusing them into an image or feeding them to instruments that can analyze their secrets. Through visible light telescopes, we see stars and galaxies as our eyes would, only fainter and farther. Through radio telescopes, we tune in to the whisper of the cosmos at long wavelengths, the songs of cold hydrogen clouds and the ghostly crackle of remnant radiation from the Big Bang. Infrared telescopes peer through cosmic dust to find stars being born in swaddling nebulae and detect the faint glow of the most distant galaxies, whose light has been stretched to infrared by the expanding universe. Ultraviolet and X-ray telescopes capture high-energy phenomena, flares on stars, the glow of gas around black holes, the hot plasma in galaxy clusters. Each portion of the electromagnetic spectrum is like a different chapter of the cosmic story, and we've learned to read them all. The observable cosmos extends far beyond what human eyes alone can see, thanks to these extensions of our senses. Perhaps the most ancient light of all that we have observed is the cosmic microwave background, the cooled, faint afterglow of the Big Bang itself. Discovered by accident in 1965 as a pervasive microwave hiss in a radio antenna, this all-sky glow is the light from about 380,000 years after the Big Bang, when the hot plasma of the early universe finally cooled enough to become transparent and release photons in all directions. We see it now as a uniform microwave glow coming from every direction, just a few degrees above absolute zero, the oldest fossil of light, nearly 13.8 billion years old. Detailed maps of the microwave background made by satellites, COBE, WMAP, Planck, show it's mostly uniform but with tiny variations in temperature, the seeds of all future cosmic structure. This is literally a baby picture of the universe, long before stars or galaxies existed. It's a reminder that our telescopes have pushed our vision to its limit. We can nearly see the Big Bang itself. Within the observable cosmos, we have catalogued wonders beyond count. We've seen star clusters with hundreds of thousands of suns, nebulae that are stellar nurseries sculpted by winds and radiation, galaxies colliding and merging in dances that last hundreds of millions of years. We have detected planets around other stars by the subtle dimming of starlight or the wobble of spectral lines. We now know planets are common, numbering in the billions in our galaxy alone, from hot Jupiters skimming their stars to Earth-like rocks in temperate orbits. We've measured the universe's expansion and even glimpsed its acceleration due to an enigmatic, dark energy. All of these achievements flow from extending our senses with instruments and collecting the light, or other radiation, that streams through space, carrying messages from afar. Telescopes, in a poetic sense, gave the universe a voice in time. Through them, we listen to the echoes of the past. When we look at a distant galaxy cluster, we might be seeing it as it was when our own sun had not yet formed. In the faint glow of a red-shifted galaxy, we might be witnessing an event that occurred shortly after the dawn of time. The observable cosmos is a time capsule cosmos. The phrase observable universe also reminds us of limits. Light from extremely distant regions hasn't had time to reach us in the 13.8 billion years since the Big Bang, so there are horizons we cannot see beyond, at least not yet and maybe not ever, if the expansion accelerates. This doesn't mean those regions don't exist, just that they lie beyond our view. So the observable cosmos, everything we can see or detect, is still potentially only a piece of a larger whole. But it is grand enough, about 93 billion light-years across today, accounting for expansion, containing perhaps 2 trillion galaxies. Each of those galaxies, in turn, contains billions or trillions of stars, and around many of those stars orbit worlds we are only beginning to discover. Looking up from Earth, a small creature on a small planet, we now can perceive structures and events on scales our ancestors never imagined. We have essentially pulled back the curtain of distance. And what we found is a universe that is dynamic and changing. The sky is no longer a fixed backdrop. It is a living history. Every point of light is a story unfolding. Some star being born in a nebula, another nearing its death as a red giant, a galaxy swirling in a gravitational dance with a neighbor, a supernova shining briefly like a cosmic firework. We catch these events mid-stride, like reading random pages from a vast novel. Telescopes allowed us to no longer be passive inhabitants of the cosmos, but active witnesses to its grand story. Each night an observatory opens its dome and points its giant eye outward. We extend our reach farther in space and further back in time. We do this not for conquest, but for understanding, to fill in the chapters of the cosmic story from the beginning until now. And through these observations, we have come to see the universe not as static, but as an unfolding tale with a beginning, middle, and ongoing narrative. Having surveyed what we can see, the stars and galaxies and background glow, we noticed a grand pattern in how matter is arranged on the largest scales. Galaxies are not scattered randomly. They form a vast cosmic web of filaments and voids. To this we now turn, the large-scale structure of the universe, the cosmic web that gravity built, seeded by tiny quantum ripples from the dawn of time. The cosmic web. On the grandest scales, the universe is organized into a vast cosmic web, a structure both simple and intricate, like lace stretching across unimaginable distances. If we could zoom way, way out beyond our galaxy, clusters of galaxies would begin to outline a pattern. Galaxies are not evenly sprinkled through space, but collected in filaments, sheets, and dense knots, clusters, with huge voids between them where few galaxies reside. The cosmos, viewed from afar, resembles a web or sponge, bright threads and nodes of matter surrounding dark, empty bubbles. Gravity is the master architect of this cosmic web. Over billions of years, gravity drew matter together, amplifying tiny primordial irregularities into the vast structures we see now. In the early universe, matter was nearly uniform, with slight denser spots here and there, imprinted as those tiny temperature ripples in the cosmic microwave background. As the universe expanded and cooled, these denser spots, seeded by quantum fluctuations and stretched by inflation, exerted a bit more gravitational pull, drawing in surrounding gas and dark matter. Over time, the slightly denser regions grew into filaments and clumps. The empty regions gave up matter to the crowded ones and became enormous voids. Imagine flying through a slice of the universe a few billion light-years across. For millions of light-years, you might see almost nothing, traversing a void where only the occasional dim galaxy or wisp of hydrogen appears. Then, ahead, you'd see a filamental chain of galaxies stretching across space like a gossamer strand. Drawing closer, that filament resolves. It's a chain of galaxy clusters connected by thinner tendrils of galaxies. You follow the filament to a nexus, a rich cluster of galaxies where filaments intersect, perhaps like the Coma cluster, containing thousands of galaxies swarming around a common center. From that hub, multiple filaments radiate out, each leading to other clusters. This is the cosmic web, clusters, nodes, connected by filaments, separated by voids. It's akin to the structure of a sponge or foam, an interlocking network of walls and channels. Our own Milky Way lies within this web. It is part of a small cluster, the local group, which in turn is on the outskirts of a larger Virgo cluster. That cluster is part of a filament that stretches toward the Great Coma cluster. In fact, astronomers have mapped our local section of the cosmic web and found that our local group, Virgo cluster, and other nearby clusters are all part of a supercluster system they've named Laniakea, Hawaiian for immeasurable heaven. Gravity is drawing our local group, including the Milky Way and Andromeda, toward the Virgo cluster and all of Virgo and its neighbors toward an even larger concentration called the Great Attractor. Our galaxy, in the far future, will drift along the web into those larger structures, though perhaps not before dark energy's expansion halts that motion, an evolving contest between expansion and gravity. One of the striking things about the cosmic web is how empty the voids are. Some voids span hundreds of millions of light years with almost no galaxies. In contrast, the filaments and clusters are crowded. In massive clusters, galaxies can be just tens of thousands of light years apart, very close in cosmic terms, and space between them is filled with hot, X-ray emitting gas, heated by the gravity of the cluster. The filaments themselves contain not just the galaxies we see, but also lots of dark matter and diffuse gas connecting cluster to cluster. In fact, simulations and observations suggest that most of the ordinary matter, atoms in the universe, resides not in galaxies, but in the filamentary tendrils of warm, hot intergalactic medium, WIM, threading the voids. It's like an invisible scaffold. The galaxies are like dewdrops on a spider web, outlining it, but much of the web itself is faint and hard to see directly, composed of thin gas and especially dark matter. Dark matter, that mysterious substance making up about 85% of the matter in the universe, is the backbone of the cosmic web. While ordinary gas can radiate energy and settle, dark matter does not radiate, so it forms large, diffuse halos. It was dark matter that first clumped due to gravity, with ordinary matter later falling into the gravitational wells the dark matter created. In supercomputer simulations of cosmic structure formation, one starts with a nearly uniform distribution of dark matter, with tiny random density fluctuations, and lets gravity work over billions of years. The result is a filamentary network, extremely similar to what large galaxy surveys observe. The bright nodes in such simulations correspond to where clusters of dark matter, and later galaxies, form. The long dark strands correspond to filaments of dark matter along which galaxies and clusters align. The empty regions correspond to voids evacuated of matter. It's a beautiful example of emergent order. Out of near uniformity emerges complexity, a cosmic web, simply from the action of gravity over time. Tiny fluctuations in density, originating from quantum jitters in the infant universe, became the template for everything. Stars, galaxies, clusters, the web. The cosmic web is the largest pattern we know. It shows that on the grandest scales, the universe has a structure, homogeneous and isotropic, only when averaged over truly enormous volumes, but locally clumpy in a sponge-like way. It's often said that the universe on very large scales looks the same everywhere, the cosmological principle. And it's true that if you average over hundreds of millions of light years, one region is much like another in terms of galaxy counts. But zoom in a little less and the web stands out. Homogeneous only in a statistical sense, but in reality threaded and bubbled. It's intriguing to note parallels between the cosmic web and other networks. The distribution of matter in the universe, as revealed by galaxy surveys like the Sloan Digital Sky Survey, bears a resemblance to the neural networks in brains, or the large-scale structure of the internet. Hubs and spokes, clustering of connections. This might just be a coincidence of pattern. Nature finds similar solutions to connectivity problems, or possibly a hint of deep universal principles of self-organization. When scientists compared the network properties of the cosmic web and the network of neurons in a brain, they found tantalizingly similar complexity and distribution despite the difference in scale by 27 orders of magnitude. It's a reminder that simple laws, like gravity's inverse square attraction and expansion of space, can create intricate structures mirrored elsewhere in nature. Crucially, the cosmic web is not static. It's still evolving. Over time, gravity will continue pulling matter along filaments into clusters. The rich get richer, clusters accumulate mass, and the voids get emptier. Superclusters may merge into even larger structures, sometimes called hyperclusters, though there's a limit. Eventually, dark energy's accelerated expansion will push galaxies away from each other faster than gravity can overcome. It's thought that in the far future, 100 billion years or more, distant clusters will recede beyond our observable horizon, effectively isolating each remaining cluster or group as its own island universe. At that point, any cosmic web structure beyond our local cluster will be unobservable. The larger pattern will be lost to view, though it will still exist beyond our reach. For now, however, we live at a time where we can map the cosmic web, see its glory, and use it to test our theories of cosmology. Understanding the cosmic web helps answer profound questions. How did the universe transition from the near-uniform fireball after the Big Bang to the rich hierarchy of structure we see now? The answer: the interplay of gravity, pulling matter into structure, and expansion, spreading things out, created a foam-like arrangement. Tiny fluctuations grew to filaments, matter flowed like rivers into cluster basins, and vast quiet voids were left where nothing much happens. Having journeyed from our planet to the galaxy, to clusters and the cosmic web, we've framed the large-scale architecture of the cosmos. But what holds this architecture together? And what threads run through every level of this tapestry? For that, we must discuss the fundamental forces and fields: gravity, electromagnetism, and the nuclear forces, the hidden framework, underlying movement and structure everywhere in the cosmos. Forces and fields. In the grand ballet of the cosmos, 4 fundamental forces choreograph every move. They are the unseen influences that shape everything from the orbits of planets to the light in our lamps to the fusion in stars. Though invisible, they form a hidden framework that makes the universe dance. Each force is like a different instrument in an orchestra, and together they compose the music of the cosmos, from the smallest scales to the largest. Gravity is the most familiar, and yet in many ways, the most mysterious. It is the sculptor of the cosmos, the gentle but persistent pull that guided matter into spheres and orbits. Every time an apple falls from a tree, or we feel our own weight, we are feeling gravity. This same force reaches across the emptiness of space to keep the moon circling Earth and Earth circling the sun. It binds solar systems and steers stars around the centers of galaxies. It gathered galaxies into clusters along the cosmic web. Gravity is by far the weakest of the 4 forces on small scales. A tiny magnet can lift a paperclip against the entire Earth's gravity. But over large scales it dominates because it only attracts and never cancels out. Over time, its tiny tug accumulates into an inexorable current that builds structure. Einstein revealed that gravity is not a force in the traditional sense, but a curvature of space-time itself. Mass and energy bend the fabric of space and time, and objects move along those curves. The sun dents space-time, and Earth rolls around that dent like a marble in a bowl. This elegant understanding tells us gravity is the shape of the cosmos's geometry. It's what gives the universe its large-scale structure, what makes a cloud of gas collapse into a star, what pins us to our beloved Earth. Gravity is both patient and powerful. Given enough time, it can gather raw matter into galaxies or crush a star into a black hole. Largely, though, gravity is the quiet, persistent heartbeat of the cosmos, keeping worlds in their courses and the celestial architecture intact. Electromagnetism is the artist and communicator of the universe. It is the force responsible for light itself. Every beam of starlight traveling to our eyes is an electromagnetic wave. It also binds atoms and molecules. It's the reason you do not fall through the floor. The electrons in your shoes repel the electrons in the floor. Electromagnetism is vastly stronger than gravity at small scales. It's what makes magnets cling and lightning crackle, what lets compasses point north and radio waves carry music. In atoms, the electromagnetic force binds negatively charged electrons to positively charged nuclei, forming atoms. It causes atoms to link into molecules by sharing electrons, giving us the variety of chemistry. The warmth you feel from sunlight, the colors of a rainbow, the glow of a distant galaxy, all delivered by electromagnetic radiation. Unlike gravity, which only pulls, electromagnetism can both attract and repel. Opposite charges attract, like charges repel. This push-pull interplay creates structure on the atomic and human scales. It keeps electrons whizzing around nuclei instead of flying away, and it causes molecules to have the shapes they do, enabling the complex chemistry of life. In the cosmos, electromagnetism governs the behavior of plasma, the hot, charged gas found in stars and nebulae. It sculpts the beautiful filaments of glowing gas in nebulae and the majestic arcs of solar flares rising from the sun. When we see the auroras dancing near Earth's poles, that's electromagnetism at play. Charged particles from the sun, guided by Earth's magnetic field into the upper atmosphere, causing molecules to glow. Electromagnetic fields fill space around planets and stars. For instance, the sun's magnetic field, carried by the solar wind, creates a protective heliosphere around our solar system. On Earth, the electromagnetic force is the foundation of technology, electricity, electronics, wireless signals, and biology, chemical bonds, nerve impulses. In a cosmic sense, if gravity is the weaver of the cosmic tapestry, electromagnetism provides the vibrant colors and textures. It gives matter structure and allows the universe to be visible and radiant. The strong nuclear force is the powerful glue of the atomic nucleus. Working at tiny scales, the size of an atomic nucleus or smaller, it binds protons and neutrons together despite the electromagnetic force trying to push positively charged protons apart. Protons naturally repel each other strongly, since like charges repel, and within a nucleus, they are extremely close. It is the strong force that acts like cement to hold these protons and neutrons tightly bound. It is the strongest of the four forces in terms of raw strength, but it operates only across minuscule distances, about the diameter of a proton. Beyond that, its influence drops virtually to zero. Think of it as Velcro that sticks only at very close range. This is fortunate. If the strong force had longer reach, every atom might glom together into one giant nucleus. If it were weaker, nuclei heavier than hydrogen, which contain multiple protons, would fly apart, and the diversity of elements would vanish. In the cores of stars, when temperatures and pressures slam protons together with tremendous force, the strong force takes hold and fuses them. Hydrogen nuclei merge into helium, releasing tremendous energy. This nuclear fusion, governed by the strong force overcoming electromagnetic repulsion, is what makes stars shine for billions of years, converting a bit of mass to energy via EXMC2. The sunlight that warms your face is a byproduct of the strong force at work in the sun's heart, forging helium and releasing energy. Later, in a massive star's life, the strong force will operate on heavier elements. Carbon fuses into heavier elements all the way up to iron. But iron is the end of the line. Fusing iron doesn't yield energy, so in the final moments of a massive star, when its core is iron, the outward pressure stops and gravity causes collapse. The core implodes until the strong force between nucleons, protons, neutrons, and quantum pressures of neutrons say no further, either halting collapse and producing a neutron star, or if the star is massive enough, even the strong force yields and a black hole forms. In either case, the star's outer layers explode in a supernova, scattering heavy elements into space. The strong force in those violent moments forged all elements heavier than iron, gold, uranium, etc., which seed future stars and planets. Thus, the strong force is the creator of elements. It stitched the carbon in your cells, the oxygen in your water, the iron in your blood. Aptly named, it is stronger than electromagnetism at short range, for it must be to bind the nucleus. But outside the nucleus, we never directly sense it. It's confined to the tiny atomic realm. It's the secret fire at the center of matter, unleashed only in rare moments like inside a star or a nuclear reactor or bomb. Without the strong force, atoms beyond hydrogen wouldn't hold together, and the cosmos would be a featureless fog of particles. With it, the richness of atomic matter exists. The weak nuclear force is the most subtle and elusive of the four. It operates within atomic nuclei as well, responsible for certain kinds of nuclear transformations. In particular, it governs radioactive decay and the conversion of one type of particle into another. The weak force is the force of change. Where the strong force holds nuclei together, the weak force lets them transmute. For example, the weak force can turn a neutron into a proton, an electron, and an antineutrino. This is beta decay. This happens in naturally radioactive elements, like a carbon-14 atom decaying into nitrogen-14, emitting an electron. It also happens in the sun. In the proton-proton fusion chain, two protons fuse, and one must turn into a neutron via the weak interaction, allowing them to form deuterium, heavy hydrogen. Without that step, the sun's primary fusion cycle would stall. Thus the weak force, though feeble, is crucial. It lights the stars by enabling fusion and shapes the decay of heavy elements that heat Earth's interior. Radioactive decays of uranium, thorium, potassium contribute to Earth's geothermal heat, driving plate tectonics and volcanoes. The weak force has an incredibly short range, even shorter than the strong force, and is aptly named. It's far weaker than electromagnetism and strong force, stronger than gravity on subatomic scales, but gravity is irrelevant there. We typically notice the weak force only through radioactive decays or in high-energy particle physics experiments. It's carried by heavy W and Z bosons. It doesn't create binding structures. Instead, it allows particles to change identity. It is unique in that it can change a quark's flavor, turning a down quark to an up quark or vice versa, which is how a neutron becomes a proton. We rarely sense the weak force in daily life. It's a behind-the-scenes presence, but it's essential for the evolving cosmos. Without it, the sun wouldn't shine the way it does, and many elements produced in supernovae wouldn't form, because beta decays during those explosions create elements like gold from lighter ones. If the strong force is the builder and electromagnetism the artist, the weak force is the quiet facilitator of change, enabling the cosmic alchemy that gives variety to matter. These four forces together form the infrastructure of reality. Each has its domain of influence. Gravity dominates the astronomical realm of planets, stars, and galaxies. Electromagnetism rules atoms, chemistry, and everyday phenomena. The strong force governs the atomic nucleus and powers stars. The weak force allows the transmutations that underlie both star power and natural radioactivity. They are the threads running through the cosmic fabric, and the fields they generate fill the space around us. Modern physics describes forces via fields and exchange particles. The gravitational field, possibly with gravitons. The electromagnetic field, carried by photons. The strong force field, carried by gluons binding quarks. The weak force field, carried by W and Z bosons. But leaving such technicalities aside, what's astonishing is that these few interactions explain a vast range of phenomena. Consider how these forces all play together in a simple moment. You stand outside on a sunny day. Gravity roots you to Earth and holds our planet in orbit around the sun. Electromagnetism governs the sunlight warming your face and lets your eyes see the world in color. It also keeps the ground solid beneath your feet, electrostatic repulsion between atoms. The strong force long ago fueled the nuclear reactions that produce that sunlight, and even now holds the nuclei of your atoms together. The weak force within the sun allowed protons to turn into neutrons, ensuring the fusion cycle could proceed steadily and power the sunlight. In your body, the weak force is causing a handful of potassium-40 atoms to decay each second, emitting neutrinos that stream harmlessly into space. In that one moment, All four forces are at work seamlessly, and you remain blissfully unaware, simply enjoying the warmth. Throughout cosmic history, these forces guided the formation of structure and the dynamics of change. Gravity drew together the cosmic web and formed stars and galaxies. Electromagnetism made those stars shine and binds atoms into molecules, leading to planets and life. Within stars, the strong and weak forces together forge new elements, which are then spread by supernovae to seed planets and life. We often call them forces of nature, but one might also call them cosmic rules or fundamental interactions, the basic ways pieces of the universe interact. Understanding these forces has allowed us to deepen our comprehension of the cosmos and harness aspects of it for our use. They also inspire a sense of marvel, how elegant that four simple interactions underlie the complexity of the entire universe. Gravity, shaping a galaxy cluster or light from a quasar, 12 billion light-years away, traveling to Hubble's mirror. It's all governed by the same physics that dictates an apple falling or a magnet sticking on a fridge. It suggests a profound unity that from the smallest scales of quarks to the largest scales of galaxy superclusters, the same fundamental forces operate, just with different relative strengths and effects. There are moments in modern physics where we dream of an even more unified picture. Perhaps these four forces were once one, a single force in the extremely hot young universe that later split into four distinct facets as the cosmos cooled. This is the idea behind grand unified theories and attempts to include gravity in quantum theory. Whether nature has such a unified force or not, what stands is that from the grandest cluster of galaxies down to the tiniest atomic nucleus, these four interactions suffice to explain what we observe. When you watch the stars at night, their light reaching you is an interplay of gravity, holding those stars together, and electromagnetism, bringing their light to your eyes, and even quantum effects of atoms, allowed by electromagnetic and strong forces. These forces are the invisible poetry of the cosmos. They make the silent emptiness of space a dynamic arena. Through them, a universe that could have been chaos becomes a symphony of structure and motion. As we understand these forces, we appreciate the finely tuned balance that allows complexity to emerge. With gravity alone, matter would clump infinitely, or not form structure if universe expands too fast. Without gravity, no stars or planets would gather. Without electromagnetism, no atoms or light. Without strong force, no nuclei beyond hydrogen. Without weak, no stellar alchemy creating diverse elements. Our cosmos manages to have them all in just the right mix to give rise to the rich tapestry we see, including us, observers who can reflect on it. Armed with knowledge of the forces, we can now tell the stories governed by them. The deep time tales of stars and galaxies, their births and deaths. These will be our next focus, to see how the cosmos changes over time, how stars live and die, how galaxies evolve, and what fate awaits the universe. Time is the stage on which the forces play. And entropy, the tendency toward disorder, provides an arrow to that time. Let us now unfold the saga of deep time, witnessing the life cycles of stars and the evolving cosmos, told not in equations, but in emotions, as we connect to these distant events that ultimately made our own existence possible. Deep time. In the vast ocean of time, stars are born and die like living things. Galaxies grow and change, and even black holes have life stories. To truly grasp the enormity of cosmic history, we must step outside the human sense of time and enter epochs that dwarf our imagination. Deep time is a realm where 1,000,000 years might pass in the blink of an eye, where the dance of creation and destruction unfolds over eons, with a grandeur at once awe-inspiring and poignant. The life of a star. Picture a dark nebula in a spiral arm of the Milky Way, a cold, dusty cloud light years across, quietly drifting for ages. Within it, A subtle gathering begins, perhaps the shockwave of an ancient supernova, or the pressure of a spiral density wave triggers parts of the cloud to contract under gravity. In those shrinking pockets, gas and dust draw together, atoms crowd and collide, heating up. What was cold and dark starts to glow dull red from the heat of compression. In one such cocoon, at the center of the collapsing cloud, a new light ignites. A protostar is born. It's like a baby star, unstable, convulsing with magnetic storms, gobbling up gas from the surrounding cloud. As it grows, its core becomes denser and hotter until one miraculous moment, hydrogen atoms, squeezed and heated fiercely, begin to fuse into helium. The strong force binds them, the weak force facilitates the fusion, and a torrent of energy is released. Outward pressure from this nuclear fire balances the inward crush of gravity. The star settles into a stable rhythm. It has entered the long, middle chapter of its life, the main sequence. Our Sun is in this phase, shining steadily for about 4.6 billion years, and with roughly 5 billion to go. Throughout the galaxy, countless stars of various sizes share this fate, turning hydrogen into helium in their cores, pouring light and heat into space. They are like the adults of the stellar family, some smaller, cooler, and redder, burning fuel slowly and destined to live extraordinarily long, tens to hundreds of billions of years. Others much larger, hotter, and bluer, burning furiously and living fast. Just a few million years, cosmic mayflies among stars. As time flows, even stars must change. When a star exhausts the hydrogen in its core, the delicate balance tips. Fusion slows. The core begins to contract under gravity and heats up, while the outer layers, freed from the core's pressure, expand outward. For a star like the Sun, this heralds transformation into a red giant. In a deep-time vision, one would see the Sun swell many times its current size, perhaps engulfing Mercury, Venus, and even Earth. Its surface cools as it expands, shifting to a luminous orange-red hue, while its core grows hotter and denser until helium can fuse into carbon. For a while, the Sun will juggle new reactions, shining not with its familiar white-yellow, but with the ruby light of old age. It may pulsate gently, shedding its outer layers in concentric waves of gas and dust. In its final breaths, it will cast off those layers entirely, creating a glowing planetary nebula, an expanding shell of gas lit by the hot, exposed core at the center. That core, no longer supported by fusion, will settle into a white dwarf, a hot, dense ember, roughly the size of Earth, but with most of the Sun's mass, slowly cooling over billions of years. The nebula will disperse into the interstellar medium, seeding space with elements the Sun forged, carbon, nitrogen, and more, gifts to the galaxy for future stars and planets. The white dwarf will fade from white to yellow to orange to red to black over trillions of years, a cinder in the darkness. Unless perhaps someday it flares again by accreting matter from a neighbor, as in a nova or supernova, if it had a companion. Such is the quiet finale for a medium star like the Sun. For stars much more massive than the Sun, the end is far more spectacular and violent. These titans, over about 8 solar masses, burn their fuel at a frantic rate, living only a few million years. They blaze hot and blue-white, and after fusing hydrogen to helium in their core, they proceed to fuse helium into carbon and oxygen, then heavier elements in layered shells, neon, magnesium, silicon, all the way to iron. Iron is a dead end. Fusing iron consumes energy instead of releasing it. So a massive star builds up an iron core like ash from a fire. Once the core is largely iron and grows to about 1.4 solar masses, it can no longer support itself against gravity. Thermal pressure and electron degeneracy pressure fail. In literally seconds, the core collapses. Protons and electrons mash together into neutrons, releasing a flood of neutrinos. The core implodes until neutron degeneracy and repulsive nuclear forces halt the collapse abruptly, and then it rebounds. This rebound, aided by neutrino pressure, launches a shockwave outward. The star's outer layers are blown off in one of nature's most cataclysmic events, a supernova explosion, briefly outshining all the billions of other stars in its galaxy. The debris, now rich in those heavy elements beyond iron, which are forged in the incredible temperatures of the explosion, is hurled into interstellar space. This supernova remnant will eventually mix with other gas and perhaps condense into new stars and planets. Meanwhile, the collapsed core remains. If the star's initial mass was moderately high, say 8 to 20 solar masses, the core becomes a neutron star, an object of mind-boggling density, about the size of a city, but with more mass than the Sun, composed mostly of neutrons. It spins rapidly. A newborn neutron star might rotate dozens of times per second, and has a powerful magnetic field, often becoming a pulsar that beams radiation like a lighthouse. If the star was extremely massive, the core collapse overwhelms even neutron degeneracy. No known force can withstand the gravity, and it continues collapsing into a black hole, a region of space-time from which nothing can escape. In either case, something remarkable happens. A once brilliant star ends in a tiny, dark remnant. If a neutron star or black hole is in a binary system, it might later accrete matter and produce X-ray emissions or further explosions, novae, X-ray bursts, etc. This cycle of stellar birth, life, and death is the heartbeat of cosmic evolution. Stars are not eternal. They are born, they mature, they grow old, and they die, often in a way that seeds the next generation. When the first generation of massive stars in the early universe died as supernovae, they produced and scattered the first heavy elements. Those enriched the gas from which new stars formed, including ones smaller, like the Sun, that could host planets with complex chemistry. Indeed, our solar system formed about 4.6 billion years ago from a cloud seeded by earlier stars' deaths, evidenced by radioactive isotopes in meteorites that are products of supernova explosions. Thus, we live in a universe where death begets new life. Supernovae create the raw material for planets and life. Even the gentle expulsion of a red giant's envelope, forming a planetary nebula, returns material to space that can be recycled. Carl Sagan's famous line, "We are made of star stuff," speaks literally true. The carbon in our proteins, the calcium in our bones, the iron in our blood, were all forged in stellar furnaces and spread by stellar deaths. Deep time connects to our very being. The evolution of galaxies. Stars live within galaxies, and galaxies themselves change over cosmic time. Galaxies can be thought of as ecosystems of stars, gas, dust, dark matter, and star clusters, all interacting. Over billions of years, galaxies grow and transform, often through mergers with other galaxies. The early universe likely had many smaller protogalaxies that gradually coalesced into the large galaxies we see today. The Milky Way, for example, has consumed several smaller galaxies in its history, and continues to do so. We see streams of stars in our halo that are remnants of devoured dwarf galaxies. Spiral galaxies like ours likely formed when smaller gas-rich pieces merged, and the combined rotation settled into a disk. Galaxies evolve from one form to another. Two spiral galaxies merging may form an elliptical galaxy, losing their delicate spiral structure in a gravitationally violent embrace and triggering massive bursts of star formation as gas clouds collide and coalesce. Over time, ellipticals, which have little cold gas left after such bursts, become dominated by older, redder stars and have less ongoing star formation. Spirals, if left relatively unperturbed, can keep forming stars as they draw gas inward or accrete from their surroundings, but they too can run low on fuel. Our Milky Way is fated, in about 4 to 5 billion years, to merge with the Andromeda Galaxy, which is currently about 2.5 million light-years away and closing in at 110 km. Despite the enormous number of stars in each galaxy, hundreds of billions, individual stellar collisions are very unlikely due to vast interstellar spaces. However, the gravitational interaction will distort both galaxies dramatically. Over a few billion years, the two will likely settle into a single larger elliptical galaxy, sometimes dubbed Milkomeda. Simulations show their beautiful spiral arms will be thrown into chaotic streams. A burst of star formation may occur as gas clouds slam together. Ultimately, a more spheroidal distribution of stars will result. For any creatures alive then, perhaps far descendants of humanity or other intelligences, the night sky will transform. At first, Andromeda grows larger, then the sky fills with a blaze of new star formation and tidal tails of stars, and eventually it settles to a hazy glow of an elliptical galaxy filling the sky. The sun, by then a red giant or white dwarf, will find itself in a vastly altered cosmic neighborhood. Galaxies also evolve internally. Young galaxies, in the early universe, were often clumpy and irregular, forming stars at high rates. The peak of star formation in the cosmos was around 3 to 4 billion years after the Big Bang. Since then, star formation has generally declined as the big galaxies used up much of their readily available gas. Today, many large galaxies, especially ellipticals, are red and dead, forming few new stars, populated mainly by the aging population born in earlier epochs. Spirals like the Milky Way still form stars, but at a moderate pace. The Milky Way turns about 1 solar mass of gas into new stars per year. Small dwarf galaxies, especially if isolated, may still be forming stars slowly or have spurts of activity when tidal interactions occur. Galaxies can also lose gas. In clusters, where dozens to thousands of galaxies reside, a small galaxy, speeding through the hot intracluster medium, can have its gas stripped, like a breeze blowing leaves off a moving car, a process called ram pressure stripping. This leaves it without fuel for new stars, turning a blue spiral into a reddish gas-poor one. Or a galaxy might have its gas consumed by rapid starbursts, or sucked into a central black hole's accretion disk, active galactic nucleus, again quenching star formation. We observe many cluster galaxies that have this quenched appearance. Speaking of black holes, nearly every large galaxy has a supermassive black hole at its center, with masses from millions to billions of suns. In youth, when gas was abundant, these black holes likely powered quasars and active nuclei, sometimes expelling jets and winds that influence their host galaxies. The interplay between central black holes and galaxy evolution is an area of active research. These black holes might help regulate star formation by heating or expelling gas, a kind of feedback. Thus, galaxies change both from external events, collisions, interactions, and internal dynamics, using up or losing gas, the effects of supernova and black hole feedback. Over deep time, the population of galaxies shifts. Fewer spirals exist now than in the past. Some have merged into ellipticals, and more ellipticals and lenticulars, disk galaxies without much gas or spiral structure, populate clusters. In the far future, as mentioned, accelerating expansion will isolate groups of galaxies. It's thought that in about 100 billion years, if dark energy remains constant, distant galaxies beyond our local group will have moved out of view, leaving future observers in our locale with only the merged Milkomeda galaxy and its satellites visible, effectively a cosmic island, with little evidence of the wider universe's existence. They would see an apparent static cosmos of one galaxy, unaware of the greater cosmic web that we now behold. Black holes and the long future. Among the remnants of deep time, black holes stand as perhaps the most enigmatic. A star leaves behind a neutron star or black hole. Galaxies have supermassive black holes at their cores. Over extremely long times, black holes may become the dominant living things as stars burn out. A typical stellar black hole, tens of solar masses, will persist far, far longer than the current age of the universe. But even black holes aren't forever. Stephen Hawking showed that they slowly evaporate by emitting Hawking radiation due to quantum effects near the event horizon. A black hole, the mass of the Sun, would take 1067 years to evaporate, an almost inconceivable span. Supermassive black holes take even longer, 100 plus years. But on the scale of deep time beyond star-filled eras, after all normal matter decays or is ejected, eventually black holes too will leak away their mass and disappear in a final burst of radiation. So imagine the stages of deep time. Now, the stelliferous era, full of stars shining. In about 100 trillion years, the last stars, likely low-mass red dwarfs and white dwarfs cooling into black dwarfs, will fade, the end of the era of starlight. What follows is sometimes called the degenerate era, the universe populated by degenerate remnants, white dwarfs, neutron stars, black holes, and cold brown dwarfs and planets. Collisions among these remnants could occasionally spark new activity. Two brown dwarfs merging might form a brief red star, or two white dwarfs colliding might ignite a supernova. But overall, it's a slow, dim time. Over quadrillions of years, gravitational encounters will gradually unbind most remaining stellar remnants from galaxies. Stars get flung out into the intergalactic void, one by one. Planets will fall into white dwarfs or be ejected. Eventually, even our Milky Way remnant, whatever it becomes after merging with Andromeda, will lose most of its constituents, and the galaxy as a gravitationally bound system will dissolve. Then comes the black hole era. After 1040 or 1050 years, depending on mass distributions, virtually everything left gravitating in lumps are black holes, from massive ones to possibly an army of micro-black holes, if any were created, though unlikely naturally. They slowly evaporate. The universe is dark except perhaps for occasional flashes when black holes finish evaporating, or rare collisions between remnants. After an absurdly long time, all black holes evaporate too. We reach the final stage, some call the dark era. Only subatomic particles remain, mostly photons, neutrinos, electrons, and positrons, spread so thin across an ever-expanding cosmos that on average years of travel would be required to hit another particle. The temperature everywhere will be effectively absolute zero, apart from quantum fluctuations. The cosmos will have reached maximum entropy, no available free energy to do anything, essentially a quiet heat death. This long view, from bright Big Bang to faint heat death, is mind-bending. It makes our era of galaxies and stars and life seem like a fleeting springtime in the cosmos. And indeed, it is. Yet knowing this timeline can inspire an even greater appreciation for the now. We live in a special time when the universe is full of light and complexity. The deep future, though bleak in prospect, is fortunately trillions of times farther away than the current universe's age, so for all practical purposes, the cosmos will remain lively far, far longer than it has existed so far. Deep time narratives invite us to face both the resilience and impermanence of the cosmos. Stars die, but their remains fertilize new stars. Galaxies collide destructively, but forge new stars in the process. Even black holes might eventually die, but perhaps releasing whatever information they held. Through an emotional lens, these are stories of cosmic reincarnation and renewal, followed eventually by an end of things. An arc with a beginning and end, just as mythologies had, but on incomprehensible scales. To an immortal being watching eons pass, the universe would appear as a vast garden. Stars bloom like cosmic flowers, some short-lived and brilliant, others steady and enduring, then wither, their substance becoming the seeds of new blooms. Galaxies grow by gathering these blooms, sometimes pruning each other in collisions, and eventually many go to seed themselves as diffuse clouds. The garden analogy falters by the end of time, when darkness covers all. But by then, the garden had given all it could. For us, understanding deep time is at once enlightening and sobering. It contextualizes our brief lives in something far larger. It reminds us that change is constant. No arrangement of matter lasts forever. Yet it also shows how creative the universe has been in the time allotted, going from near uniform gas to conscious beings pondering it all. Now, with a grasp of deep time's canvas, we can zoom back to our human scale and ask, how do we, conscious flickers in this vast unfolding, fit in? The next chapter turns to the emergence of something arguably as remarkable as any galaxy, consciousness, which allows the cosmos to reflect on itself. Scale. As we zoom from the cosmic to the minute, we encounter a remarkable truth. Patterns repeat and echoes sound across vastly different scales. The universe is structured hierarchically, from subatomic particles up through atoms, molecules, planets, stars, galaxies, and the cosmic web. And while each layer has its unique phenomena, sometimes the small and large reflect each other in surprising ways. Imagine scaling down from human size. Shrink 1 billion times. You stand at the edge of an atom, electrons whizzing in a cloud around a tiny nucleus. The nucleus, if you peeked in, is itself a swarm of protons and neutrons, bound tightly by the strong force. Dive further. Inside a proton, you'll find quarks darting amid a sea of gluons. This is a world measured in femtometers, 10 to 15 me, and less, a far cry from everyday scales. Now zoom out, past human scale to planetary and beyond. The Earth orbits the Sun at 150 million km. The Sun orbits the center of the Milky Way, 27,000 light-years away, along with hundreds of billions of other stars. Our galaxy, 100,000 light-years across, is one of perhaps 100 billion in the observable universe. The largest coherent structures we see, walls of galaxies and voids, span a few billion light-years. That's a factor of about 10,040 from the Planck length, 10 to 35 maths, believed to be a fundamental scale of quantum gravity, to the observable universe's diameter, 10 to 27 maths. Yet through this immense range, the same fundamental principles operate. Gravity holds planets in orbit much as it holds galaxies in clusters, just with different relative influences of other forces. Electromagnetism binds an electron to an atomic nucleus and similarly governs the structure of a star via plasma interactions. The forces of nature are scale-blind. They work everywhere, with only their effects modulated by environment. The small and the large often mirror each other. Consider a hydrogen atom, a tiny nucleus with electrons in orbit, historically likened to a miniature solar system. That analogy isn't perfectly accurate. Quantum mechanics shows electrons are in fuzzy probability clouds, not neat orbits. But the structural motif of a central mass with orbiting bodies recurs. Electrons around nuclei, moons around planets, planets around stars, stars around galaxy centers. The binding forces differ, electromagnetic versus gravitational, but the resulting patterns have a visual resonance. A spiral galaxy with its arms may evoke the swirl of water down a drain, or the spiral of a hurricane, not because they are caused by the same reasons, gravity versus pressure and Coriolis forces, but because rotating systems often settle into spirals to conserve angular momentum and form density waves. One fascinating comparison: the cosmic web of galaxies and the network of neurons in a brain have been noted to share similar filamentary structures. One is billions of light-years across, the other confined to a skull, but both are vast networks shaped by growth rules. A 2020 study even quantified similarities in the distribution of matter in the cosmic web and neural networks. While obviously the physics differ, the abstract analysis of connectivity showed parallels in complexity. It's a reminder that complexity can emerge from simple rules at multiple scales, sometimes yielding convergent structures. Our sense of scale is very limited to the human range. We measure in meters and seconds suited to our everyday life. But the universe extends far above and below those. A cosmic perspective forces us to accommodate scales where our intuition fails. It's mind-bending that an atomic nucleus, with its protons and neutrons, is as small relative to us as the sun is large relative to us. We sit roughly in the middle of logarithmic scales, about 10 2 meters in size. On a log plot from the Planck length to the universe, humans are not far from center. In a way, we have 1 foot in the micro-world. We can examine things as small as molecules and atoms with effort, and 1 foot in the cosmic. We can see galaxies and clusters with our telescopes. Perhaps this accident of scale is what allowed us as a species to comprehend things far beyond our direct sensory realm. We evolved in a world where both small and large phenomena affected us, from grains of sand to the cycling sun and moon, giving us curiosity in both directions. And indeed, modern science is a triumph of exploring both the very small and very large. By going down to subatomic scales, we've uncovered the fundamental particles and forces enabling technologies like electronics and nuclear energy. By going up to cosmic scales, we've discovered the Big Bang, cosmic expansion, and the age of the universe. The fact that the human mind, a small-scale object itself, can grasp scales 10-20 times smaller and 10-20 times larger than itself is astonishing. It's a testament to mathematics and imagination that we can conceptualize things so far outside direct experience. Another connection across scales is that the very large was seeded by the very small. Quantum fluctuations, random tiny variations at the subatomic level, during the epoch of inflation in the extremely early universe, were blown up to macroscopic size, laying down the pattern for the cosmic web. Thus, the distribution of clusters and voids we see today is in part a fossil record of quantum events in the first 10 to 30 seconds of the universe. The microscopic shaped the telescopic. This is almost poetic. The initial graininess on the quantum level became the literal grains, galaxies, in the cosmic structure. Conversely, understanding large-scale processes often helps reveal small-scale physics. For example, observing the nuclear reactions in the Sun via neutrinos and helioseismology confirmed our knowledge of particle physics, like the properties of neutrinos. The solar neutrino problem and its resolution in neutrino oscillations showed neutrinos have mass, a small-scale property discovered by looking at a star. Cosmology data, like the microwave background and element abundances, provide evidence for particle physics phenomena, like the existence of relativistic species, neutrinos, in the early universe. In summary, the cosmos is truly fractal-like in its wonders. Patterns and principles iterate, and insight at one scale often informs another. We find ourselves at an intermediate scale, but equipped with tools and reason to traverse the extremes. By doing so, we realize that we are not isolated at our scale. We are made of subatomic particles, and we orbit a star in a galaxy. We contain multitudes of atoms, and we are part of something larger, the universe. Embracing this multi-scale reality adds to our awe. The next time you hold a salt crystal, consider that within its tiny cubic structure lies a microcosm of electromagnetic forces and quantum rules, not entirely unlike the gravitational lattice of galactic clusters spanning millions of light years. The salt's sodium and chlorine atoms form a repeating pattern, just as galaxies form a weave in space. Patterns at vastly different scales can still rhyme. Now, stepping back from scale and structure, we venture into what might be the strangest aspects of the cosmos, those that challenge our understanding not just of size or shape, but of reality itself. Black holes that warp space-time, mysterious dark matter and dark energy that we detect only indirectly, hypothetical wormholes that might tunnel through space-time, and other unknowns that remind us how much more there is to learn. It's time to explore the strange cosmos, the mysterious components and possibilities that push the boundaries of known physics. The strange cosmos. For all that we have learned, the cosmos still guards many secrets. In fact, the more we've discovered, the more we've realized how much lies in darkness, hidden from direct perception. The night sky we see, with its stars and galaxies, is only a thin slice of reality. The rest is filled with mysteries, unseen matter and energy, space-time oddities, cosmic phenomena that challenge our intuition. Among these enigmas are black holes, dark matter, dark energy, and the hypothetical wormholes and parallel universes that tantalize physicists and philosophers alike. These are the strange elements of the cosmos that make it not just vast, but deeply mysterious. Black holes, the abyss of space-time. Perhaps nothing in the universe is as foreboding and fascinating as a black hole. Imagine a star 10 times the sun's mass reaching the end of its life. Its core fuel spent, it collapses under its own weight. If nothing stops the collapse, and for a massive core nothing will, it shrinks past the formation of a neutron star, past any known stable form, to a point, a singularity, of seemingly infinite density. All that mass is now concentrated in zero volume, and gravity around it becomes so intense that within a certain radius, the event horizon, not even light can escape. A black hole is born, an object with a one-way surface. Cross the event horizon, and you cannot return or send a message out. To the outside world, you effectively vanish. Black holes take our understanding of physics to the edge. According to Einstein's general relativity, mass curves spacetime. A black hole is an extreme curvature where spacetime essentially pinches off. Time and space swap roles in a sense. Moving forward in time inevitably carries you inward toward the singularity if you're inside the horizon. Quantum physics adds further mystery. At the event horizon, quantum effects can create particle pairs, leading to Hawking radiation, meaning black holes aren't completely black. They glow faintly and lose mass over time. We have strong evidence black holes exist. Stellar black holes announce themselves by gravitational effects on companions and by emitting X-rays when consuming gas. We have imaged the shadow of a 6 billion solar mass black hole in galaxy M87 via the Event Horizon Telescope, seeing a ring of light from hot gas and a dark center where the hole's gravity prevents light from coming directly to us. We see stars at the center of our Milky Way whipping around an invisible 4 million solar mass object at speeds of thousands of km/h. Definitely a supermassive black hole. So black holes are not just theoretical. They are out there. Commonplace, in fact. Every large galaxy likely has one, and many stellar remnants become black holes. They distort reality around them. Clocks near a black hole run slower relative to far away. To a distant observer, a clock falling toward a black hole appears to tick ever slower and essentially freeze at the horizon, though the clock itself experiences falling through normally. If you fell in, past tidal forces ripping you apart, if it's a small hole, you might have some time to observe near the singularity, but ultimately you'd be crushed, and what's inside the horizon is cut off from our universe, so it's like you've left our reality. Black holes are strange because they present a breakdown of our laws. A singularity is a sign that general relativity gives infinite results, meaning the theory breaks down there. It's expected that quantum gravity, a future theory uniting GR and quantum mechanics, will resolve what happens at the core. Do singularities exist, or are they replaced by something like a quantum fuzz or bounce? Also, do black holes destroy information? Quantum theory says information, the specifics of matter that fell in, should be preserved in some form. This has led to the famous black hole information paradox. Many physicists now think information does escape in subtle form via Hawking radiation or is stored in correlations, meaning black holes might not erase information entirely, no cosmic delete button, just very scrambled output. Even more exotic is speculation that a black hole could connect to another region of space-time, a wormhole. In principle, the mathematics of GR allow an Einstein-Rosen bridge connecting two black holes, or a black hole and a hypothetical white hole, essentially a tunnel. But such wormholes, if they exist, would be unstable. They'd pinch off unless held open by negative energy, exotic matter. We have no evidence wormholes exist naturally. They might be purely theoretical or require technology far beyond us to stabilize. Still, they captivate the imagination as cosmic shortcuts or even time machines, since wormholes potentially could allow travel back in time, raising paradoxes. Dark matter, the hidden mass. In the 1970s, astronomer Vera Rubin measured how fast stars orbit in the outer parts of spiral galaxies and found something odd. They were moving as fast as stars closer in. According to Newtonian gravity, stars far from the galactic center should orbit more slowly if most mass is concentrated in the center, like planets in the solar system. Instead, galaxy rotation curves flatten out, indicating there's much more gravity, and hence mass, in the outskirts than can be accounted for by visible stars and gas. Similarly, clusters of galaxies have galaxies moving too quickly to be held together by the visible mass alone, and gravitational lensing, the way clusters bend background light, indicates more mass than seen. The conclusion: most of the matter is unseen, dubbed dark matter. Dark matter seems to interact gravitationally, but not, or extremely weakly, via electromagnetic or nuclear forces. It doesn't emit, absorb, or scatter light, hence dark. It's not made of atoms. It's something else, likely some kind of particle left over from the Big Bang that we have yet to detect in the lab. It outweighs normal matter roughly 5.1 in the universe. It's the scaffolding on which galaxies formed, as discussed in the cosmic web. Without dark matter, our models struggle to form galaxies as observed, and structures might not hold together. Despite decades of trying, we haven't directly observed dark matter particles on Earth. Various underground detectors have looked for them hitting nuclei, without confirmed success yet, or created them in colliders. We infer their existence from their gravitational effects. The leading hypothesis is that dark matter is some kind of WIMP, weakly interacting massive particle, left from the early universe, or possibly an axion, a very light particle, or something more exotic like a dark sector with its own forces. But so far, it's a shadowy presence, clearly there, yet elusive. Some have proposed alternative gravity theories, like MOND, modified Newtonian dynamics, or various relativistic extensions, to eliminate the need for dark matter by changing how gravity works at galaxy scales. While these can fit some galaxy rotation curves, they struggle with cluster lensing and the cosmic microwave background data that strongly support the dark matter paradigm. The simplest consistent explanation remains a dominant component of unseen matter. So, to an extent, we live in a shadow universe. Only about 1/6 of matter is the familiar atoms that make up stars, planets, and us. The rest, plus an even larger fraction in dark energy, which we'll get to, is hidden. It's humbling. All the glowing galaxies are like a froth on a vast, dark ocean of matter. Without that ocean, though, the froth wouldn't exist. Dark matter's gravity was essential to gather normal matter into galaxies. Dark energy, the runaway expansion. In 1998, two teams measuring distances to far supernovae made a shocking discovery. Distant type Ia supernovae were dimmer than expected, indicating they were farther than they should be if the universe's expansion were slowing down. Put simply, the expansion of the universe has been speeding up in the last few billion years. This was the opposite of what most expected. Gravity from matter should slow expansion. The cause was dubbed dark energy, a mysterious form of energy that fills space and drives accelerated expansion. It's often associated with the cosmological constant L concept that Einstein once introduced and famously discarded as a blunder when he thought the universe was static, now revived as a physical reality. Dark energy is even more enigmatic than dark matter. It constitutes about 68% of the universe's total energy content. We don't know what it is. If it's a true cosmological constant, it's an inherent property of space. Every cubic meter of vacuum has some fixed tiny energy, around 6 by 10 nars to 10 joules, that doesn't dilute as space expands. So as space grows, more vacuum means more total energy, causing expansion to accelerate. Alternatively, dark energy might be a field that can change over time, sometimes called quintessence, or something even more exotic, like an effect of other dimensions or a flaw in GR on huge scales. So far, all observations, supernova, cosmic microwave background, large-scale structure, are consistent with dark energy being a constant property of space, with an equation of state parameter, WL1, in cosmological terms. If it remains so, the fate is an ever-accelerating expansion. Galaxies outside our local group will recede faster and faster until they become unreachable and eventually invisible. Dark energy seems to have become dominant a few billion years ago. Prior to that, matter's gravity was slowing expansion. But as the universe expanded, matter diluted, density dropping as volume increases, whereas dark energy, as a constant density, did not. Eventually, matter's influence waned and dark energy took over, causing expansion to accelerate. Why dark energy has the value it does is a huge puzzle. Quantum zero-point energy calculations naively predict a cosmological constant, 10^120 times larger, which would have blown the universe apart instantly after the Big Bang. A gross discrepancy, one of the biggest in physics. Something, perhaps a cancellation mechanism we don't understand, leaves a small residual that is our dark energy. That's a major unsolved problem. If dark energy is constant, the universe will approach a de Sitter state, exponential expansion forever. If it's not constant, who knows? Some theorize dark energy could decay or even reverse, leading to a big crunch or oscillation, but no evidence of such behavior yet. So we live in a universe where about 95% of its content is in two invisible forms, dark matter and dark energy. It's as if we have a book where only some letters are visible and the rest are in invisible ink. We're trying to read the story from the few visible letters and a lot of blank spaces. Yet the visible letters, stars, galaxies, etc., give us enough clues through their dynamics and arrangements to infer what's missing. Wormholes and other wild ideas. The notion of wormholes, shortcuts through space-time, has long captured imagination. Solutions of Einstein's equations, like the Schwarzschild wormhole, which is the non-traversable mathematical connection in a black hole solution, or the traversable Morris-Thorne wormholes that require exotic matter with negative energy, indicate such tunnels are not forbidden by general relativity outright. But whether nature actually makes any is unknown. If cosmic strings, defects in space-time from early universe phase transitions, or certain quantum fluctuations occurred, some think it might be possible a few wormholes were spawned, but they'd likely collapse quickly or be extremely tiny. No evidence exists for any. If one could stabilize a wormhole, it could allow faster than light travel, effectively by taking a shortcut, or even time travel, depending how the wormhole mouths move relative to each other. But physics as we know it strongly suggests causality violations are not allowed. Time travel leads to paradoxes, though closed, time-like curves can exist in theory. Most physicists suspect some deeper principle prevents actual time machines. Another wild idea: maybe our whole universe is a patch inside a larger multiverse, where other universes have different physical constants or particles. Inflation theory suggests space might be much larger than our observable part, possibly with other bubble universes disconnected from ours. If so, maybe constants like gravity's strength or protons' mass could vary in those bubbles. That could partially explain why our constants are tuned for life, anthropic selection from many universes. But this remains speculative and arguably untestable. We can't observe other universes if they're truly disjoint. Some signatures like colliding bubble universes might imprint something in our cosmic background, but none clearly seen. It might be that what we call constants of nature are not fixed in space-time either. There are studies testing if, say, the fine structure constant, electromagnetic strength, or electron-proton mass ratio has changed over cosmic time by analyzing ancient light. So far, results are mostly consistent with no change, or changes so slight they remain debated. If any drift exists, it's very tiny, meaning the laws today were essentially the laws 10 billion years ago. All these strange aspects, wormholes, multiverses, varying constants, stretch the boundaries of the known. They are at the edge of science and veer into philosophy at times because they're hard to verify or falsify. Still, exploring them is valuable. It expands our conception of what might be possible and forces us to confront the assumptions in our accepted theories. Embracing mystery. Confronting the strange cosmos instills humility. We see that our knowledge, while vast compared to the ancients, may still be scratching the surface. We uncovered dark matter and energy by their gravitational footprints, but we don't yet know their identities. We theorized black holes from relativity, then found they are real astrophysical objects, yet at their core lies the need for a new theory, quantum gravity, to understand singularities. We use quantum mechanics and relativity daily in our devices and GPS, yet their reconciliation into one framework eludes us, hinting at deeper layers of reality. The strange elements of the cosmos are clues that the story isn't finished. There are chapters of physics yet to be written, perhaps by future generations. And yet, rather than these unknowns making the universe seem alien, they can also inspire a sense of being part of a grand quest. We alive today are among the first generation to know that dark matter and dark energy exist. Perhaps one day a child today will solve the riddle of dark matter in a lab experiment or theory. We stand on a threshold where the cosmos is telling us there's more here than meets the eye. In grappling with the strange, we also find a reassuring continuity. Every time our view expanded or was challenged by Copernicus, by Hubble, by dark energy's discovery, we eventually integrated it and found our understanding actually deepened and often benefited humanity. Imagine modern tech without quantum mechanics or relativity, which were once strange new ideas. So there is faith, born of experience, that confronting the unknown is worthwhile, and reality, however strange, is ultimately comprehensible, as Einstein mused. Now, having explored the structure and mysteries of the external cosmos, we turn inward to perhaps the most remarkable outcome of cosmic evolution, ourselves, conscious beings capable of reflecting on the cosmos. We examine how the universe, through life and mind, has awakened to itself, and what that means for meaning and perspective. Consciousness. At some point in cosmic history, the cosmos became aware of itself, on at least one planet and perhaps countless others, a collection of atoms organized in such a way that it could ponder the very stars that made its constituents. This phenomenon, consciousness, is the most complex and mysterious form of order we know. Through us, and beings like us, the universe has eyes to see and minds to contemplate its own vastness. Carl Sagan put it poetically, "We are a way for the universe to know itself." The journey to consciousness was gradual and took billions of years on Earth. Simple life emerged at least 3.5 billion years ago in Earth's oceans, likely as self-replicating molecules that became enclosed in membranes, primitive cells. These life forms could sense and respond. Even a bacterium will move toward nutrients or away from harm. That's a rudimentary form of awareness, not thought, but biological feedback. Multicellular life allowed differentiation, specialized cells for sensing, like light-sensitive patches that became eyes, and for processing, simple neural nets. By the Cambrian explosion, 540 million years ago, complex animals with eyes and nervous systems filled the seas, presumably experiencing basic perceptions. Fast forward, vertebrates developed more complex brains. Some lineages crawled onto land. In mammals, the brain's cortex expanded, enabling memory, learning, and emotion. At some indeterminate point, early humans or their ancestors achieved self-awareness, an ability not just to feel or learn, but to know that they know, to reflect on one's own existence. Consciousness is hard to define but intimately known to each of us. It's the subjective experience of internal and external reality. It's the I am behind your eyes, the experiencer of your life. Scientifically, we map its correlates, brain patterns, neural oscillations, integrated information, but we don't truly understand how the grey matter of the brain produces the bright light of consciousness. This is the hard problem of consciousness. Yet, it undeniably does, at least in humans, and likely other animals to varying degrees. From a cosmic perspective, consciousness is profound because it seems qualitatively different from unconscious matter. The ingredients that make a human, oxygen, carbon, hydrogen, nitrogen, calcium, etc., are common in the cosmos, in air and rock and sea, but arrange them in the exquisite complexity of a living cell, then an organ, then a brain, and something novel emerges: mind. It raises a question. Is consciousness a fundamental aspect of the universe? Some philosophers and physicists have toyed with panpsychism, that consciousness might be a property of matter under certain conditions. Or is it an emergent phenomenon requiring a certain level of complexity? Either way, the potential for mind was built into the cosmos from the start, in the sense that the laws of physics allowed matter to self-organize into conscious forms. When the universe was a hot plasma, it had no structures at all, let alone life. But it cooled, matter clumped, stars forged heavier elements, planets formed with complex chemistry, life sparked and evolved, and eventually, those ancient atomic nuclei, born in the hearts of stars, became part of a thinking being that can look back and say, "Wow, I come from the stars." The cosmos became aware of its origins through our minds. This confers a sense of purpose, in a way. Not an externally assigned purpose, but a role we naturally play. We are the cosmos, in one of its latest evolutionary phases, marveling at itself. When we discover things about the universe, it is literally the universe discovering itself. Our joy of comprehension is the universe taking joy in self-comprehension. Consciousness also heightens the emotional stakes of cosmic knowledge. Without conscious beings, the grand universe simply is, with no one to admire a nebula or fear a black hole. With consciousness, beauty and terror enter the scene. Think of the first humans fearful of eclipses or awestruck by the Milky Way. The cosmos evokes feelings now because we feel. Through us, the universe has emotion and meaning, at least locally. A nebula is not objectively beautiful, but we find it so, giving aesthetic dimension to existence that wouldn't exist without minds. Many scientists and philosophers suspect life and possibly consciousness might not be unique to Earth. If biology is a natural outcome on wet, rocky worlds under the right conditions, and evolution often fosters intelligence given enough time, then perhaps the cosmos teems with other conscious beings. They may not be human-like, but they could wonder and seek as we do. Perhaps the universe has many centers of consciousness scattered among the galaxies, a kind of cosmic self-awareness shining in many places. Or perhaps not. Maybe intelligent life is extremely rare. We don't know yet. Either answer, teeming life or cosmic solitude, is profound. If we are among many, What a grand community awaits discovery, though distances are forbidding. If we are alone, or nearly so, what a precious flame of awareness we bear, and what responsibility to not squander it. Consciousness gives the universe a way to know time, in a meaningful way too. Without minds, time just passes. With minds, the passage of time is felt. We have memory of the past and anticipation of the future. We seek patterns and thus uncover cosmic history, like figuring out the Big Bang, and cosmic future, heat death or other fates. In a sense, by becoming aware of deep time, we have extended the reach of consciousness to the entire lifespan of the universe. Mentally, we travel to the beginning and to hypothetical ends. The universe through us can contemplate its entire existence, almost like how we as individuals reflect on our own lives. There is also a contemplative aspect. Many find that recognizing we are the universe coming to consciousness can be spiritually meaningful. It collapses the divide between me and world. In a cosmic sense, the distinction is indeed arbitrary. We're made of the world and return to it. As conscious beings, we can feel empathy not just to other living things, but to the stars and the atoms, feeling a unity with all. Some spiritual traditions echo this scientific truth. We are one with the universe. As we move forward, conscious of our conscious role, we might ask, what next for the cosmos and consciousness? Will our awareness fade when humanity, or life, ends, or will it spread? Some dream of humanity expanding to other planets, carrying consciousness further through the cosmos. In doing so, giving the universe more places where it can reflect on itself. Others consider that artificial intelligence might carry consciousness, or at least intelligence forward, even if biological life fails. It's a speculative territory, but the point remains. Through our minds, the universe has reached a level of self-reflection, and what we do with that is, to some extent, up to us. Having considered mind and meaning, let's pull back one last time to the broadest perspective. Is our universe the only one? Or could there be a multitude, a multiverse? And is the structure of reality fundamentally made of something like information or math, rather than tangible matter? These are deep questions at the intersection of physics and philosophy. We touch on them briefly, as they color the ultimate context in which our cosmos might reside. The multiverse. Is our universe unique, or one of many? For ages, universe meant all there is. But modern physics has opened the door to the idea that our universe might be a bubble in a froth of countless universes. A multiverse. This concept arises from several lines of thought. One is cosmic inflation, the idea that a fraction of a second after the Big Bang, space expanded exponentially fast. Inflation theory, in many versions, suggests that inflation didn't end everywhere at once. It ended in patches, like our universe, while other regions kept inflating, budding off other bubble universes. If eternal inflation is correct, our universe may be one domain among an indefinitely large, possibly infinite number of domains, each a universe in its own right, with potentially different properties. Another motivator is fine-tuning. We observe that certain fundamental constants, like the strength of electromagnetism or the dark energy density, have values in a narrow range that allows complexity, galaxies, stars, life, to exist. It's puzzling why they have just those life-permitting values. One possible explanation is the anthropic principle combined with a multiverse. If indeed many universes exist with varying constants, we naturally find ourselves in one of the minority that by chance has the right conditions for observers, because only such universes get observers. It's like we shouldn't be surprised to live on Earth rather than on Jupiter. Only Earth had the proper conditions for our kind of life. Similarly, maybe only a small fraction of universes have viable physics for any form of complexity, and of course, we must be in one of those. If the multiverse idea is true, reality is much bigger than we can see. Our observable cosmos, the 93 billion light-year bubble of space we can currently observe, would be just a tiny patch in an inconceivably vast inflating space that contains other bubbles beyond our horizon. We cannot directly communicate with or travel to those other universes. Space between us and them is still inflating, or they're causally disconnected. But their existence would answer some otherwise intractable why questions by essentially saying everything happens somewhere. We see what we see because those conditions are necessary for us to exist. In some multiverse scenarios, the basic laws might differ. Perhaps one universe has a slightly stronger, strong force, which might mean no hydrogen, all protons fuse into heavier elements quickly, or a slightly weaker electromagnetic force. Maybe stars can't form because fusion won't ignite. There might even be universes with different numbers of spatial dimensions or different particle types. The possibilities are vast in principle. We don't know if physical constants can vary like that. But string theory, for instance, predicts a landscape of possible vacuum states with different properties, and eternal inflation could populate different regions with different vacuum states, hence different constants and particle physics. It's almost a philosophical question. Are these other universes real if we can never observe them? Some say if a theory that predicts them also robustly predicts things we can observe, and the theory is validated, then we must accept whatever else it entails, like unseen universes. Others argue that non-disprovable entities are not within science's remit. Currently, the multiverse is a hypothesis, intriguing, sometimes seemingly implied by theories but not confirmed. Parallel to the cosmological multiverse is the idea from quantum mechanics of the many worlds interpretation, that every quantum event that has multiple outcomes, electron goes left or right, spawns branches of reality for each outcome. In that view, all possible histories consistent with quantum probabilities play out in a vast branching of universes. This is a different beast than the inflationary multiverse. These universes occupy the same space but in different quantum branches, rather than separate bubbles of space. But interestingly, both ideas paint a picture of numerous alternate realities. If both were true, it could be an unimaginably enormous collection of universes, bubble universes, each with internal branching quantum worlds. These ideas challenge our notion of uniqueness. It might make one feel small. Not only are we one tiny planet in a vast universe, but our entire universe might be one grain of sand on an endless cosmic shore. But one can also find it empowering. If indeed our universe is rare enough to permit life, how lucky we are to experience it. If universes are countless, then the creative potential of reality is truly without limit. Whatever can happen will happen somewhere, perhaps many times over. One might ask, how does multiverse thinking affect daily life or meaning? Perhaps not much. True or not, it doesn't change the tangible universe we interact with. But it adds another layer to the grand perspective, maybe even our entire cosmic cosmos, a journey through space and time. In the beginning, there is nothing but darkness. For ages untold, after the birth of the universe, there is no light, only a silent void and the cooling embers of the Big Bang. Imagine this primordial darkness. No stars, no galaxies, just an endless night stretching millions of years. Yet in that darkness, something is stirring. Gravity is gently pulling together clouds of pristine hydrogen gas, gathering and squeezing them in invisible hands. Deep in one such cloud, pressure mounts, atoms collide, and heat rises. There is a tremor in the void, a hint of radiance forming, still hidden. Then, suddenly, light. A blinding spark erupts where there was none before. In an instant, the first star ignites. The cosmic dark ages end in a flood of starlight. It is the universe's first sunrise. A lone star has begun to shine, pouring out photons into the black abyss. Soon, another star kindles, and another. The newborn cosmos sprinkles itself with tiny islands of light. The darkness of creation is pushed back by these early fires, and the cosmic dawn has arrived. What was once cold and black is now dappled with the warm glow of starlight. Eons later, on a small young planet orbiting a later generation of those stars, there comes another first sunrise. Picture Earth over 4 billion years ago, a barren world of rock and boiling seas under a choking sky. The air is thick with volcanic fumes and the dust of creation. As the planet cools, its skies begin to clear. One morning, the clouds part to reveal a brilliant glow on the horizon. Dawn breaks over Earth's primordial landscape. For the first time, sunlight bathes the craters and steaming oceans of our world. The infant sun climbs over the horizon, and day begins on Earth. The planet's surface, once lit only by lava and lightning, now knows the gentle illumination of a star. That first sunrise would have been an alien scene. No life to witness it. Only chemistry and stone. Yet it was a harbinger. From that day onward, every living creature on Earth would be born to a world warmed and lit by a star in the sky. Our sun had arrived in our heavens, and nothing would ever be the same. Ancient reverence. From the moment humans first opened their eyes under its golden light, we have felt the sun's power. Long before science, we knew in our bones that our lives depended on that glowing orb. Every dawn brought light and warmth. Every dusk brought its absence. In the sun's daily rising and setting, ancient peoples saw the dance of gods and the rhythm of existence. So across cultures and centuries, mythologies blossomed around the sun. Our star became our deity, our timekeeper, our source of life in story and song. In ancient Egypt, the sun was Ra, the falcon-headed god who sailed across the sky by day in a great barge and descended into the underworld at night. Each sunrise was Ra's triumphant return after vanquishing the darkness. Egyptians tilted their faces to the dawn and felt the touch of a divine father. Far to the east, Vedic hymns of India praised Surya, riding a chariot led by 7 shining horses, bringing light, dispelling evil, and watching over all creatures. In the clear air of the Andes, the Inca honored Inti, the radiant patron of empire, believed to be an ancestor of their kings. Temples and treasures were devoted to Inti's glory. The sun's daily journey inspired vivid imagination. The Greeks envisioned Helios, a titan crowned with rays, steering a fiery chariot drawn by stallions across the sky from east to west. Each evening, Helios would descend at the horizon and embark on a nightly voyage in a golden cup back to the east, so he might rise again. His Roman counterpart Sol, and later Sol Invictus, the unconquered sun, symbolized continuity and victory over darkness. In Japan, the sun was personified as Amaterasu, the great goddess of light. When she hid herself in a cave out of grief, the world was plunged into darkness until the other gods lured her out, restoring light and hope. Every culture found its own language for the sun's gift. The Norse spoke of the goddess Sol, forever chased by a giant wolf across the sky. At the end of days, they feared the wolf would catch her, and darkness would consume the world. The Aztecs offered beating hearts to Tonatiuh, the sun of the 5th age, believing only constant sacrifice could fuel the sun's strength to rise each day. In Mesopotamia, mighty Shamash not only lit the day, but also saw all, becoming a god of justice, shining his light on the truth. The Chinese told of 10 suns that once scorched the world until only one was left to give gentle light. The sun has been a wheel of fire, an eye in the sky, a divine torch carried by various hands in human imagination. We built monuments to chase the sun's movements. On Salisbury Plain, Stonehenge's stones were carefully aligned with the solstice sunrise, so the first ray on midsummer's morning would pierce straight to the heart of the circle. In temples and pyramids across the world, from Abu Simbel in Egypt to Angkor Wat in Cambodia, architects aligned doorways with the sun, capturing its light on sacred altars on specific days of the year. To ancient peoples, these moments when the sun's light perfectly struck their creations felt like communion with the heavens. The sun told them when to sow and when to reap, marking seasons with its ever-changing arc in the sky. A stable sun meant abundance. An eclipse or an unexplained dimming could instill terror that the gods were angry or the end was nigh. In prayer, in ritual, in art, humanity paid homage to this bringer of life. We bowed to dawn and rested at dusk. We celebrated the sun's return at winter solstice festivals, when days would lengthen again. Even monotheistic religions kept echoes of sun worship, halos around saintly heads, Sunday as a holy day. The sun was our first clock and calendar, a golden heartbeat to measure our days. Yet, for all its importance, the true nature of the sun remained a mystery to our ancestors. They saw a bright disk that moved and gave heat, but what it was, a chariot wheel, an eye of a god, a hole into the realm of fire. No one knew. Still, they revered it rightly as the great sustainer. They intuited that without the sun's daily presence, the world would be cold and dead. In their myths, the sun was often benevolent, but sometimes fickle or wrathful, a reflection of how its light could bless crops or, in drought, become a searing curse. Even today, if you've ever stood at dawn and felt the first rays warm your face, you can sense that ancient awe. The sun touches something primal in us. It's no wonder early humans worshipped it. They were reaching out to understand and thank the very thing that made their lives possible, from myth to science. In time, humanity's curiosity outgrew our myths. We began to seek a more concrete understanding of the sun. Gazing up, we asked not only who carries the sun across the sky, but what is the sun, really? Our journey to the answer spanned centuries. It led us from seeing the sun as a unique heavenly jewel to recognizing it as one among countless stars, and ultimately to uncovering the nuclear fire at its heart. It started with a radical idea that the sun, not Earth, was the center of things. Renaissance astronomers like Copernicus and Galileo dared to put the sun at the center of our solar system, dethroning Earth. This heliocentric model slowly overturned old cosmic orders, and with them, the special pedestal of our sun as something apart from the stars. In 1610, Galileo turned his telescope to the sun and saw dark blemishes crossing its face, sunspots. The discovery that the sun had spots and that they moved, showing the sun's rotation, was shocking. It meant our perfect heavenly light had imperfections. The sun was not a flawless god, but a dynamic, changing sphere. Galileo's observations, nearly blinding work in an era without proper filters, marked humanity's first scientific look at our star. As the centuries turned, more questions arose. What was the sun made of? How could it burn so brightly for so long? By the 19th century, even as scientists catalogued the sun's spectrum and found new elements, the sun's power source remained an enigma. Some theorized it was a burning coal or contracting gas, but calculations showed chemical fire or gravity alone could not sustain the sun for millions of years, let alone the billions required by Earth's geology. The sun simply put out too much energy. The answer arrived in the 20th century. The sun shines by thermonuclear fusion. In its core, light elements are fused into heavier ones, releasing prodigious energy. In essence, the sun is a gigantic nuclear reactor. This realization dawned slowly. Scientists like Arthur Eddington first guessed it, that the pressures at the sun's center could force hydrogen atoms to merge into helium. Later, others worked out the details of those reactions. At long last, we understood. The sun was not a divine flame or a burning ember of creation. It was a star, a common type of star, powered by extraordinary processes. The gulf between our sun and the stars in the night sky closed. They were the same kind of thing. Our sun is just our star, the one we happen to live next to. This was a humbling shift. The sun went from being the singular light of our existence to one of perhaps 100 billion lights in our galaxy. The word sun itself simply means any star that has planets in orbit. Astronomy taught us that each star in the sky is another sun for someone, and perhaps each sun in turn could warm other worlds. The universe became both bigger and more intimate. We found kinship between our sun and the countless stars shining out there. So our sun is a typical star, but it is also unique to us. It is our sun, the anchor of our solar system, the gravitational linchpin that holds 8 planets, dozens of dwarf planets, millions of asteroids, and trillions of comets in its family. It contains 99.8% of all the mass in the solar system. All the planets, moons, and debris are mere crumbs from the sun's table. This brilliant sphere dominates our cosmic neighborhood. Today, instead of worship, we show reverence through exploration. We study the sun with a fleet of spacecraft and a cadre of telescopes. We have learned more in the last few decades than in all of human history before. Yet the more we uncover its scientific secrets, the more our sense of wonder grows. The sun is not a simple ball of fire. It is a complex living system with a heartbeat and moods, with mysteries and surprises still in store. We have traded mythic poetry for factual poetry, one might say. The truth of the sun, as a star powered by fusion, variable and even violent, is as awe-inspiring as any legend. With our modern understanding, we can tell the sun's story from its birth among the stars, through its present life, giving glow, and on to its far future fate. We can connect the nuclear reactions in its core to the warmth on our skin. We can appreciate how the sun's tantrums create ethereal auroras on Earth, and how, someday, the sun will transform and force life as we know it to change or perish. This is the saga of our sun, one star in an endless sea, yet everything to us. Now, let us journey into the life of the sun itself. Let us peel back the layers of our star, travel to its core, and ride the energy outward. We will watch the sun's surface seethe and erupt. We'll follow its influence across space to Earth and beyond. We'll look back to the sun's birth and forward to its death. And in doing so, perhaps we'll come to see the connection between that nuclear furnace and the beat of our own hearts, born of cosmic clouds. Every star has a story that begins in darkness. The sun's tale starts around 4.6 billion years ago in a cold, diffuse cloud of gas and dust on the outskirts of the Milky Way galaxy. Picture a vast nebula, light years across, full of hydrogen, helium, and faint traces of heavier elements. For ages, this cloud drifted quietly. Then something happened to disturb its peace. Perhaps a shockwave from a distant supernova slammed into it, or maybe 2 clouds collided. Whatever the trigger, it caused a region of the cloud to compress. Within that region, gravity took hold. A denser clump drew in more and more material, growing denser and heavier in a runaway process. As the gas fell inward, it began to spin, an ice skater pulling in her arms, rotating faster and faster. The collapsing clump flattened into a swirling protoplanetary disk, like a cosmic whirlpool, with most of the mass collecting at the center. That center grew ever hotter and denser as gas piled on. This was the protostar that would become our sun, still shrouded, not yet shining by its own light, but getting warmer and warmer. Around this infant protostar, the remaining disk of gas and dust would eventually clump to form planets, moons, and asteroids, the embryonic solar system. But at this early stage, all attention is on the burgeoning star, child at the disk's core. As more mass crushed in, the protostar's core pressure skyrocketed. When the core reached about 15 million degrees Celsius, a profound transformation occurred. Hydrogen nuclei began to fuse. At first, it was just a trickle of fusion reactions sparking to life. But soon, a threshold was crossed. The protostar effectively ignited in a sustained way. The inward crush of gravity was met by the explosive outward pressure of new energy. The darkness of the collapsing cloud was pierced by the first true starlight of our sun. It was born, a full-fledged star, now stabilizing into the long, steady burn of its youth. If we could have witnessed it then, we'd see a new star appearing where none had shone before, hidden deep in its natal cloud until its light blew away the cocoon. Perhaps it glowed a bit bluer and larger at first, shedding excess heat, then settled to the yellow-white we know. Our sun joined the cosmic landscape as one more pinprick of light in the galaxy. Around it, the leftover disk began to cool and condense. Within tens of millions of years, that disk formed the planets, including Earth, making the sun not only a star, but the center of a solar system. Interestingly, our sun wasn't born alone. Star formation often happens in clusters. Multiple stars form from different clumps in the same giant cloud. Our sun likely had sibling stars, born in the same stellar nursery. For a few 100 million years, they might have been loosely bound, a cluster of suns drifting together. But over time, they scattered across the Milky Way, each going its own way. Somewhere out there in the galaxy, far from us now, there may be stars that once twinkled alongside the infant sun before destiny separated them. Now they are just anonymous stars in the night sky, their shared origin with our sun obscured by time and distance. So the sun's birth was both a solitary emergence from darkness and part of a communal genesis of many stars. From gravity's pull and nature's want of equilibrium, a star was born, the furnace was lit, and in that lighting, the stage was set for everything to come, the formation of Earth and the eventual spark of life in the sun's warm glow. The hearth of fusion, at the core of the newborn sun, and still today, in the mature sun, an astonishing process unfolds: thermonuclear fusion. This is the engine of the star, the secret of sunlight. Yet for all its technical sound, we can think of fusion in human terms. It is the sun's heartbeat, the rhythmic source of energy that keeps it alive. Deep in the sun's center, the conditions are almost inconceivable. The pressure is millions of times the atmospheric pressure on Earth. The temperature is around 15 million degrees C. The hydrogen gas that composes most of the sun is crushed so tightly that it becomes a dense plasma, atoms stripped of electrons, nuclei packed shoulder to shoulder. In this extreme environment, hydrogen nuclei, which are simply protons, are forced close enough together to overcome their natural repulsion. When two protons slam together hard enough, they can stick and transform, ultimately creating a helium nucleus out of 4 hydrogen nuclei through a series of reactions. In that alchemy, a tiny bit of mass is lost and converted to pure energy. This is happening constantly in a chain reaction known as the proton fusion cycle. Every second, the sun's core fuses about 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons, converted to energy as radiant light and heat that eventually makes its way out of the sun. 4 million tons of matter turned into energy every single second. It's a number almost too large to grasp. It's like detonating billions of nuclear bombs each second just to produce the sunlight we find so gentle here on Earth. How can we imagine this furnace? Perhaps as a stellar heart, throbbing out energy, or as a vast forge where the simplest element, hydrogen, is forged into helium, like an eternal smithy. Or think of it as a boiling cauldron of creation, where matter and energy are freely interchangeable. The core is only about a quarter of the sun's radius, but it holds nearly half the sun's mass, densely packed and actively burning. It is here that the sun's life is decided. So long as there is hydrogen to fuse, the sun will shine steadily. Fusion in the sun is a surprisingly subtle dance. not a runaway explosion. The star's self, gravity contains and regulates it. If the core produces a bit too much energy, the core will expand slightly, cooling and slowing the fusion rate. If it produces too little, the core contracts, heating up and boosting fusion. This feedback keeps the Sun in an equilibrium that has persisted for billions of years. In this way, the Sun is stable, a gently humming engine rather than a bomb. The heat flowing outward provides pressure to counter gravity inward. A beautiful balance. Gravity compresses, fusion energizes. One tries to collapse the star, the other tries to blow it apart, and in the middle the Sun holds steady, like a suspended ball in a fountain stream. While hydrogen fuses to helium in the core itself slowly accumulates helium ash. Over the Sun's lifetime, helium has been building up inside. But the Sun has so much hydrogen and burns it relatively slowly that even after 4.6 billion years, it's nowhere near running out. Our Sun is comfortably middle-aged, still rich in fuel for about another 5 billion years of hydrogen burning. It's mesmerizing to think. Every photon of sunlight, every beam that warms your skin began as an act of nuclear fusion in the Sun's core. Each one was born in a flash of two atoms becoming one, releasing energy. The sunlight is literally the product of mass turned into energy deep within our star. The Sun's core is a closed realm, hidden from direct view. Yet it is the very definition of vitality for the Sun. If we call the Sun the heart of our solar system, it's apt because within the Sun lies a heart of its own, pumping out the light that feeds the planets. This fusion hearth is not static. It subtly pulses, not in dramatic throbs, but through waves and oscillations that ring through its interior. Through a field called helioseismology, scientists have detected sound waves echoing inside the Sun, caused by bubbling convection and other processes. By studying these solar seismic waves at the surface, we infer details about the core's conditions. In essence, we can listen to the Sun's heartbeat and learn its rhythm and structure. It's like ultrasound for a star, listening to its ringing to map its insides. And what have we found? That the Sun's core rotates a bit faster than its surface, and that it's maybe a touch hotter or cooler in spots than expected, but by and large, our models of fusion hold true. With the core burning steadily, the Sun has entered what's known as the main sequence phase of its life, the long, stable period in which a star fuses hydrogen to helium. For a star of the Sun's mass, this period lasts about 10 billion years. Our Sun is nearly halfway through that allotment. During this time, it changes only gradually, growing slightly brighter over eons as helium accumulates in the core. But for now, the Sun shines with a steady golden consistency that has nurtured life on at least one world. Journey of light. Consider now a single photon, a particle of light, born in the Sun's core. It begins its life as a high-energy gamma ray emitted from a fusion reaction. In that first moment, it's a blazing bit of energy flying outward, but its journey to escape the Sun is anything but straightforward. The Sun is incredibly dense in its interior, and this newborn photon's path is immediately halted by a collision with a nearby proton or electron. It gets absorbed and re-emitted or scattered in a random direction. It zigzags and ricochets through the crowded interior like a pinball in an infinite machine. The Sun's interior has layers like an onion. From the core out to about 70% of the Sun's radius lies the radiative zone. Here, the dominant mode of energy transfer is by radiation, photons carrying energy outward, but it is a slow diffusion process. The photon we imagined will undergo an enormous number of scatterings in the radiative zone. It bounces a short distance, hits a particle, gets sent in a new direction, maybe even back inward, then out again, over and over. It performs a drunken random walk toward the surface. The distances between collisions grow longer as the gas gets thinner farther out. perhaps only a fraction of a millimeter near the core between collisions, stretching to a few centimeters near the radiative zone's outer edge. It is an epic and tedious journey. How long does it take for a photon to get out? Ironically, something that travels at the speed of light can take on the order of thousands or even hundreds of thousands of years to escape the sun. Estimates vary, but by many accounts, the sunlight that reaches your eye today began its trip in the sun's heart when humanity was in its infancy or before. In a poetic sense, the daylight illuminating an ancient Egyptian carving might have been generated around the time the sun's energy currently warming us was starting its long march outward. The sunlight is ancient by the time it emerges. In contrast, once it's free, it only takes a brief 8-minute sprint across space to reach Earth. Thus we say, every sunrise is powered by ancient light. Eventually, our photon reaches the outer 30% of the sun's interior, the convection zone. Here, the density has dropped and the temperature gradient steepened such that gases can't transfer heat by radiation alone. They begin to circulate like a boiling pot of water. Hot plasma near the radiative zone rises toward the surface, cooling as it goes, then sinks once it has given off its heat, only to be reheated and rise again. These convection currents are enormous, each cell the size of a continent or larger. In cross-section, they look like granules or kernels. Indeed, if you look at the sun's surface with a high-powered telescope, you see a granulation pattern, a carpet of bright blotches with darker boundaries. Those bright blotches are the hot tops of convection cells where material is upwelling. The dark outlines are cooler, sinking material. The scale is staggering. Individual granules are on the order of 1,000 kilometers across. For our photon, being caught in the convection zone is like catching an express elevator after wandering in a maze. The energy gets swept up by the moving plasma and ferried upward much more directly. Within days or weeks, a blob of plasma can rise from the bottom of the convection zone to the visible surface, carrying its photon energy with it. When that plasma finally reaches the surface, the photosphere, it radiates the energy away as new photons of mostly visible light. Our original photon might have been absorbed and its energy redistributed into many lower energy photons by now. By the time energy leaves the sun, it is mostly in the form of visible light with a spectrum peaking in the greenish yellow, perfect for our eyes, which evolved under this light. In essence, the sun converts the furious gamma rays of the core into a brilliant white light at the surface, a bit like allowing scalding steam to cool into warm water by the time it touches you. The photosphere is what we typically refer to as the sun's surface. Although being gaseous, the sun has no solid surface. It's the layer where the plasma becomes transparent enough for photons to finally escape into space. It's only a few hundred kilometers thick, razor thin compared to the sun's 700,000 kilometer radius. The photosphere's temperature is about 5,500 degrees in its upper layers, cooler than deeper inside, but still hot enough to glow bright. This is the light we see. When you safely project or filter an image of the sun, the features you observe, the mottled granulation, any sunspots, reside in the photosphere. As our photon escapes the sun and zips into the solar system, another ghostly traveler flies outward too, neutrinos. These nearly massless particles are produced in astronomical numbers by fusion reactions. Unlike photons, neutrinos interact so weakly with matter that they stream straight out of the sun's core and into space almost unhindered, reaching Earth in just over 8 minutes. Trillions pass through your body each second, unnoticed. They are like telegrams from the sun's core, confirming fusion is ongoing. We have built giant underground detectors to catch a handful of these elusive particles, and indeed, we have detected them, verifying that the sun's core is doing what our theory says. Neutrinos are essentially a direct line of sight to the sun's core, whereas photons only show us the surface. They've told us that the sun's output hasn't changed drastically in at least 100,000 years. and that our fusion calculations are correct within a few percent. So now, after an arduous journey, the energy birthed in the solar core has made it out. The sun's light is free, radiating into space in all directions. A minuscule fraction of it will intersect Earth, providing daylight and sustenance. The rest travels on, maybe to light up other planets, or just to disperse into the void. This continuous flow of energy from core to surface to space is the lifeblood of the sun. It is as if inside the sun, a story is written in energy, and that story travels for millennia to emerge as the light that then writes a chapter in the story of life on Earth. The many hues of sunlight. Step outside on a clear day and look at sunlight. To our eyes, it looks bright and roughly white or golden, depending on the time of day. But sunlight is not a single color or type of light. It is a symphony of many wavelengths of electromagnetic radiation, from high energy ultraviolet to visible colors to low energy infrared and beyond. The sun is often depicted as yellow in drawings, but in truth, the sun emits all colors of visible light blended together, which our eyes perceive as white. Our atmosphere can make the sun look yellow, orange, or red at times by scattering away the shorter wavelengths. But in space, the sun shines a near white. If we pass sunlight through a prism, it fans out into a rainbow, the solar spectrum. Every color from violet through red is present, fading seamlessly one into the next. This is the sun's visible fingerprint. Sprinkled in that rainbow, scientists have found dark lines, the Fraunhofer absorption lines, where elements in the sun's cooler outer layers absorb specific colors. By decoding those spectral lines, we learned which elements abound in the sun. Hydrogen and helium, overwhelmingly, with traces of almost every other element present in smaller amounts. In fact, those dark lines in the solar spectrum led to the discovery of helium in 1868. It was seen in the sun before it was found on Earth. The sun thus gave us helium, an element that remained hidden on Earth until later. But the sun's spectrum extends far beyond what our eyes can see. Ultraviolet radiation from the sun, invisible to us, is present in sunlight and carries more energy per photon than visible light. Most UV is fortunately blocked by Earth's ozone layer and atmosphere, but enough reaches the ground to give you a suntan or sunburn, a daily reminder that the sun outputs rays that can be both life-enabling and harmful. At even higher energies, the sun emits X-rays and even gamma rays, especially during solar flares, but those do not penetrate our atmosphere. On the other end, the sun emits plenty of infrared radiation, experienced by us as heat. Step into a patch of sunlight on a cool day and feel warmth on your skin. That's IR at work. Roughly half of the solar energy reaching Earth's surface is in the infrared. It's what warms the ground, oceans, and air. Plants reflect a lot of near-infrared, which is why they appear bright in infrared photography, but they eagerly absorb visible light for photosynthesis. The sun also emits radio waves, though relatively weakly in continuous spectrum. However, during solar flares or plasma oscillations, strong bursts of radio waves can occur, which we can pick up with antennas. Meanwhile, just below visible light is near ultraviolet, and just above violet is extreme ultraviolet. The sun emits those from its hotter regions, like the chromosphere and corona. Viewing the sun in different wavelengths reveals different stories. In ultraviolet, we see the chromosphere and lower corona as a dynamic network of loops and flashes. This is how satellites like SOHO and SDO image the sun's atmosphere and catch flares or eruptions. In visible light, we see the familiar yellow-white photosphere with sunspots, faculae, and granulation. In infrared, we can probe cooler features and sometimes see deeper into sunspot regions, and also observe the solar limb darkening effect clearly. In EUV and X-rays, we see the million-degree corona blazing from active regions, coronal loops, and coronal holes. In radio, we can study the sun's corona and even below the surface via radio emissions and detect burst events from flares. This broad spectrum underscores that the sun isn't just a static bulb of white light, but a multifaceted powerhouse. It also highlights how the sun affects Earth on many levels. UV shapes the upper atmosphere chemistry. Visible light fuels life and drives weather by heating Earth's surface unevenly. IR provides direct heat and is key to the greenhouse effect that keeps Earth warm. Interestingly, the sun's spectrum peaks in visible light, and not by accident. Our eyes evolved to be sensitive to the sun's peak output, and Earth's atmosphere has a window of transparency in the visible range. If the sun were a cooler red dwarf, peak output would be in infrared, and perhaps eyes on a planet there might evolve to see IR, or if hotter, eyes might see more UV or blue. And then there's invisible sunlight beyond the EM spectrum, neutrinos and the solar wind of charged particles. Both could be considered outputs of the sun in a broader sense. Solar wind shapes Earth's magnetosphere and is the cause of auroras, as we'll discuss. And neutrinos provide insight into the core. The solar constant is about 1,361 W/s. This is what powers essentially all surface phenomena on Earth, from winds to ocean currents, to the water cycle and life itself. It's remarkably stable, varying only 0.1% over the 11th year cycle, and maybe up to 0.3% over centuries, if at all. The sun is more stable than many stars, which is fortunate for us because even a few percent variation could profoundly affect climate. That stability is one reason complex life could flourish on Earth. Our sun is a well-behaved star, not prone to large swings in luminosity. To sum up, the sun wears many colors. It emits a broad spectrum from radio waves to gamma rays. We see just a sliver, but modern instruments have expanded our vision. This multi-wavelength view has turned the sun from a blinding disk into a rich landscape of features. A calming white photosphere here, a violent UV flare there, a shining X-ray corona above. It reminds us that reality is often beyond human senses, and only by extending them do we fully appreciate the sun's grandeur. The next time you notice the golden light of late afternoon or enjoy the colors of a sunset, remember that this show is the result of the sun's rays interacting with our atmosphere. The reds and oranges of sunset happen because blue light has been scattered out, leaving the warm tones to travel through thick atmosphere to your eyes. It's a daily demonstration of the sun's spectrum and Earth's filtering, a touch of cosmic physics in an everyday experience. The sun's surface and atmosphere. The word surface is a bit misleading for the sun, since it has no solid crust. But when we say surface, we mean the photosphere, the visible disk from which light escapes. Just above the photosphere, the sun has an atmosphere of its own, layers of gas that are even more rarefied, where fascinating and sometimes puzzling things occur. Immediately above the photosphere lies the chromosphere, a region a few thousand kilometers thick. Normally, the chromosphere is hard to see because the photosphere's glare overwhelms it. It reveals itself in certain wavelengths or during solar eclipses as a thin pinkish rim around the sun. During a total eclipse, just as the sun is almost completely covered, observers often see a red flash or fringe. That's the chromosphere emitting light, notably the red glow of hydrogen gas. Early spectroscopists called it the flash spectrum. The chromosphere is a dynamic, fiery layer. It's populated by spicules, narrow, spike-like jets of plasma that shoot up from the photosphere into the chromosphere and last only minutes. Thousands of spicules are active at any time, giving the chromosphere a jagged, fur-like appearance in certain filters. The chromosphere is also threaded with filaments and plages. The temperature in the chromosphere actually rises with height, from about 4,500 K at the bottom to perhaps 20,000 K or more at the top. This is already a clue of some extra heating beyond simple radiative loss. Above the chromosphere, there's a thin transition region only a few hundred kilometers thick, where the temperature skyrockets from tens of thousands to nearly 1,000,000 Kelvin. Immediately above that is the corona, the sun's outer atmosphere, which extends millions of kilometers into space. The corona is breathtaking. During a total solar eclipse, it's that pearly white crown we see encircling the black lunar silhouette. It's made of extremely hot, tenuous plasma. The corona is actually far less bright than the full moon. We can see it in eclipse only because the moon blocks the overwhelmingly brighter photosphere. One of the longest-standing puzzles in astrophysics is the coronal heating problem. Why is the sun's corona so hot when the sun's surface is relatively cool? Typically, if you move away from a heat source, temperature drops, like walking away from a fire. But above the photosphere, at first it drops. Then it leaps upward in the corona. It's as though you walked away from a campfire, and suddenly the air got scorching hot, far beyond the flames. Scientists suspect the sun's magnetic field is the culprit. The sun's surface and interior churn with electrically charged plasma, which twists magnetic field lines. These fields carry energy upward. There are a few ideas on how they deposit heat. Magnetic reconnection. Tangled magnetic field lines in the corona can snap and rejoin, releasing energy as heat. This could heat pockets of plasma to high temperatures. Waves. The turbulent motions of the photosphere might send upward Alfvén waves or other magneto-hydrodynamic waves that carry energy. When these waves reach the less dense corona, they could dissipate their energy as heat. Microjets or current sheets. Various small-scale dynamic phenomena in the lower corona might rapidly pump energy into coronal plasma. The Parker Solar Probe is actually gathering data relevant to this, diving into the corona to measure fields and particles directly. Early results have observed strange zigzag switchbacks in the magnetic field and bursts of plasma, providing clues. The solar orbiter has imaged omnipresent tiny flares on the solar surface, which might be part of the heating story. The corona is structured by the magnetic field. Above active sunspot regions, you get bright coronal loops in X-ray and EUV images, arches of plasma confined by magnetic lines, glowing at millions of degrees. In polar regions, or places with open field lines, you get coronal holes, which appear dark in X-ray EUV because they're cooler and less dense. These are sources of fast solar wind streams. The corona continuously expands into space, creating the solar wind. At some point, the plasma becomes so thin that particles escape the sun's gravity. That's the beginning of the wind. The boundary where the sun's atmosphere transitions to solar wind is not sharp. Essentially, the corona is the solar wind's birthplace. Now moving back inward, the chromosphere and corona aren't static shells. They are in constant flux. Solar flares often manifest as bright ribbons in the chromosphere and dazzling loops in the corona. When we monitor the sun in H-alpha, we primarily see chromospheric structures, filaments, plages, flares at their origin, and spicules at the limb. The photosphere, though cooler than the layers above, is where sunspots reside, and those spots have intense magnetic fields that shoot up into the corona, linking the layers. Think of sunspots as the visible feet of magnetic flux tubes that rise into the corona. Energy stored in those tubes can be released higher up. Our vantage from Earth's surface usually just shows us the bright photosphere. But with specialized solar telescopes and space observatories, we've managed to study these atmospheric layers intimately. The Solar Dynamics Observatory, for example, continuously images the sun in multiple wavelengths, giving us a 24/7 view of the chromosphere and corona dancing and flaring. It's inspiring that a total solar eclipse, one of nature's grand spectacles, was the key for humans discovering the chromosphere and corona well before the space age. During the eclipse of 1868, Jules Janssen and Norman Lockyer independently identified that mysterious yellow spectral line. During the eclipse of 1869 and others, observers noted green lines in the corona. Eclipses basically shouted to us, "There's more to the sun than meets the eye." Now we have artificial eclipses and advanced filters to monitor these layers routinely. We've directly imaged spicules, measured chromospheric magnetic fields, and observed the corona in X-ray movies over decades. Yet, even with all this, the solar atmosphere holds mysteries. We still debate exactly how the corona gets so hot. We don't fully understand the engine behind the 11th year cycle. We have difficulty predicting flares. We can see a region is ripe, but exactly when or how big a flare will go off is not yet predictable. We've realized the sun's atmosphere can even sing. It's filled with oscillations. The corona has waves and oscillatory phenomena that we can detect as periodic brightness changes. The sun is not quiet up there. It's ringing with acoustic vibrations, albeit far too thin to carry sound that we could hear with ears. Lastly, consider the scale. The corona seen during an eclipse extends several solar radii, but the influence of the sun's atmosphere actually reaches far beyond, effectively out to where the solar wind meets the interstellar medium. In that sense, the sun's atmosphere encompasses all the space where its particles and magnetic field extend. Earth orbits well within this realm, swimming in the solar atmosphere. We're effectively inside the sun's extended atmosphere all the time, in the solar wind's bubble. That's an astounding thought. We live inside the outer atmosphere of our star. So, summing up the sun's atmospheric layers: photosphere, 100 kilometers thick, 5,800 K. What we see as the surface: sunspots, granules, faculae live here. Chromosphere, few thousand kilometers thick, 10,000 K. Reddish glow in H alpha, home of spicules, filaments, magnetic network. Temperature rises with height. Transition region, very thin, temperature shoots up to 1 million K. Corona, millions of kilometers, are 1,3 million K. Thin plasma shaped by magnetic fields, source of solar wind. Each layer is physically part of the sun, but conditions change so radically that we treat them as distinct zones. And through these layers, the sun's magnetic field is the scaffolding and the agitator. The sun's magnetic heartbeat. Peering at the sun over weeks and years, astronomers long ago noticed a curious pattern. The number of sunspots on the sun's face varies in a cycle, roughly every 11 years. At times, the sun's face is nearly clear, maybe a tiny spot, or none at all for days. This is solar minimum, the quiet phase. Years later, dozens of spots speckle the sun, some growing big enough to see without a telescope as tiny blemishes. That's solar maximum, the active phase. Then the activity wanes again. This rise and fall is the famous sunspot cycle. Sunspots themselves are regions where the sun's surface is cooler than the surroundings. A typical large sunspot might be around 4,000 K in its dark core, compared to 5,800 K in the bright photosphere. Spots often come in pairs or groups, with opposite magnetic polarity. Essentially, they are like north and south magnetic poles, poking through the photosphere. One spot will have magnetic field coming out, and the other nearby with field going in, connected by loops of magnetism above. Counting sunspots by eye and later by camera, people realized they follow this quasi-11th year oscillation. Around 1850, Rudolf Wolf pieced together historical records and came up with a sunspot number index that revealed this cycle. Today, we're in cycle 25. For perspective, cycle 24 peaked around 2014 with a modest number of spots, and then an extended quiet period occurred around 2018-2019. Now cycle 25 is ramping up, likely to peak around 2025 or 2026 with a moderate number of spots. The sunspot cycle is not perfectly regular. Some cycles are 9 years, some 14, but average have an 11. Also, the amplitude varies. Some cycles in the 20th century were very strong, while some in the 19th were weaker. The 17th century Maunder minimum was an extreme case. Very few sunspots were recorded from about 1645 to 1715, a period that coincided with cooler climate in Europe. There's evidence from carbon in tree rings that other grand minima occurred in the past. So the sun's cycle itself modulates on longer timescales. What causes the cycle? The root is the sun's magnetic dynamo, the mechanism by which the sun generates its magnetic field. The sun rotates and has huge convective motions in its outer layers, plus likely a shear layer at the base of the convection zone. The interplay of these motions stretches and twists magnetic field lines inside the sun. Roughly every 11 years, the field gets so twisted that it resets. The sun's global magnetic polarity flips. It then takes another 11 years to flip back, so the full magnetic cycle is 22 years. Sunspots are a direct manifestation of this magnetic cycle. Early in a cycle, the first spots of the new cycle appear at mid-high solar latitudes. They often come in with reversed polarity compared to last cycle's spots. As the cycle progresses toward maximum, spots appear in greater numbers and at lower latitudes. Near the peak, you might see spots even 5,010 degrees from the equator. After maximum, as the cycle decays, spots get scarcer and cluster near the equator. Then it resets. No spots at the equator, and new spots of opposite polarity start popping up back at high latitudes for the next cycle. If you plot latitude of spots over time, you get the butterfly diagram. 2 wings per cycle descending toward the equator. Sunspots come and go over days to weeks. They often emerge, grow, break apart, or explode. They often appear in active regions, an area with complex magnetic structure, including multiple spots, faculae, plages, etc. Those are the ones likely to produce flares and CMEs. During solar maximum, the whole sun is magnetically disturbed. The corona is full of bright active region loops. There are more flares, and the sun's overall UV and X-ray output is higher. At solar minimum, the corona is simpler, with big coronal holes at the poles and few bright loops, and the sun's X-ray brightness can drop to nearly nothing. It's important to note the cycle isn't perfectly uniform. Sometimes big sunspots or storms happen in the decline phase, etc. But overall, more sunspots means more potential for solar storms, and vice versa. Now, why should we care about the sunspot cycle? It's not just academic. It drives the space weather environment around Earth. During high sunspot years, we get more frequent solar flares and CMEs, meaning more auroras and geomagnetic storms on Earth, as well as more radiation hazards for satellites' astronauts. During low years, space weather is quieter, but interestingly, cosmic ray flux at Earth increases. Also, the outer atmosphere of Earth cools and contracts during solar min due to less EUV heating, which can affect satellite orbits. So even earthly systems respond to the cycle. For example, the upper atmosphere density difference between solar max and min is significant for orbiting objects. Also, one's view of the polar aurora oval expands in solar max and shrinks in solar min. Radio communications on Earth are affected by the cycle too. HF radio propagation tends to be better around solar max because the ionosphere is more ionized, while during solar min certain frequencies propagate poorly. So the sun's 11th year heartbeat sends ripples through our technology and environment. On the sun itself, the cycle orchestrates phenomena. The polarity of sunspots flips each cycle. The number of prominences, flares, sunspots, faculae all follow the cycle. Even the solar poles reverse their magnetic field at each maximum. Yes, the sun's north and south magnetic poles flip around the time of sunspot peak. That's when the global field is weakest and messy, then a new polarity builds and settles by the next min. To get a little deeper, when the sun approaches minimum, often the last spots of the old cycle linger near equator. But already by then, new spots from the next cycle might have appeared at high latitudes, so cycles actually overlap slightly. We identify cycles by when the old spots mostly vanish and new ones dominate. Magnetic oddities occur too. Occasionally, there are short breaks in cycles or irregularities. We don't fully understand the sun's long-term magnetic modulation. It might have 50-year, 100-year variations. Some predict another grand minimum could occur, but that's uncertain. The cycle also has asymmetries. Typically, one hemisphere of the sun leads or dominates in a given cycle. For instance, the north might erupt earlier and have more spots one cycle, and the south might dominate the next, etc. This is an active area of research, trying to see patterns in these differences. Now, what exactly are sunspots in physical terms? They are concentrations of strong magnetic field on the order of 0.1 to 0.4 Tesla. For comparison, Earth's surface magnetic field is about 0.0005 Tesla, so sunspot fields are thousands of times stronger than Earth's field. These fields suppress convection locally, so less hot material rises, and the area cools relative to surroundings, hence looks dark. A sunspot often has a dark core and a surrounding mottled, lighter grey area with filamentary structure. Those penumbral filaments are somewhat convective flows channeled by the field. Sunspots can be as small as a few hundred kilometers or as large as 50,000 kilometers across. Galileo's drawings show some large ones visible to the projection technique he used. The biggest tend to appear around solar max. Sunspots often appear in pairs, roughly east, west of each other. One will be magnetically north, the other south. In the next hemisphere, the polarity orientation is reversed. In the next cycle, all that flips. So, summing up, the sun has a magnetic heartbeat of 11 years. It's like a slow pulse, where every beat inverts the field. With each beat, the sun goes from calm to active to calm again. At the peak, it shows its magnetic muscles via sunspots and flares. During the lull, it's magnetically catching its breath, reorganizing for the next wave. We have kept count of these beats for centuries now, and while each has its own character, the persistence of the cycle is a remarkable feature of our star. Many stars show magnetic cycles too, but the sun's is the one we have in most detail. Understanding the cycle isn't just for curiosity. It helps anticipate periods of greater solar storm risk, plan satellite launches. It also feeds into climate discussions. Tiny solar output variations might have slight influence on climate, though current climate change is dominated by anthropogenic effects. This magnetic heartbeat will continue for a few billion more years, but as the sun evolves into a giant later, it will likely become more erratic or different. Red giants can have magnetic fields, but often not cycles like the sun's. That's far ahead though. For now, we are mid-cycle in cycle 25. In a few years, we'll likely see a lively sun peppered with spots and laced with flares, a good time for aurora watchers. Then it will calm down again. The dance goes on. Storms on the sun. The sun's magnetic cycle not only brings dark spots but also violent outbursts. When magnetic energy that's been stored in twisted field lines suddenly releases, the sun experiences storms, primarily solar flares and coronal mass ejections. These are the most dramatic manifestations of a star's magnetic wrath, and they can have direct consequences many millions of kilometers away on Earth. Solar flares are essentially gigantic explosions in the sun's atmosphere. In minutes, a localized region on the sun can release as much energy as billions of nuclear bombs. A flare brightens across the spectrum. Intense X-rays and extreme UV pour out. Visible light can even increase in what's called a white light flare, and radio waves and gamma rays might be emitted too. Flares are classified by their X-ray brightness as observed by Earth orbiting satellites. The classes are A, B, C, M, X, each a step up by factor of 10. A is very small, B small, C moderate, M medium, large, X large. Within each letter class, they use a numeric scale from 1 to 9. For example, an X2 flare is twice as strong as X1 and 4 times as strong as an M5. The biggest flares recorded by modern instruments were about X28 in 2003. The Carrington event flare in 1859 is inferred to be perhaps X-class in the 30s, though direct measurement didn't exist. What triggers a flare? Magnetic reconnection is the key. Imagine magnetic field lines arching out of a sunspot pair like loops. If these lines become stressed and tangled enough, they can snap and reconnect in a lower energy configuration, like a rubber band breaking. When that happens, all the energy that was stored in the twist of the magnetic field is suddenly released as heat, light, motion, and particle acceleration. The plasma in that region gets superheated. Electrons are hurled to near light speed, spiraling along field lines, and protons and heavier ions are likewise accelerated. In images, a flare often appears as a bright flash or set of ribbons in H, alpha, or UV on the solar disk. Then you see post-flare loops, graceful glowing arcs in the aftermath as the hot plasma cools and settles in magnetic loops. Flares can happen without a CME, especially smaller ones, but big flares often coincide with a CME. Coronal mass ejections are colossal eruptions of solar plasma and magnetic field into space. Think of it as the sun belching out a piece of its atmosphere. A CME typically involves a twisted flux rope of magnetic field that suddenly ejects, carrying with it billions of tons of coronal gas. CMEs travel at speeds from a few hundred km/s to up to 200 to 500 pounds/km/s for really fast ones. At Earth's distance, that's about 1 to 3 days of travel. We often see CMEs with coronagraphs, a halo or a bright loop structure expanding away from the sun. If a CME is coming toward Earth, we might see a halo CME. Many strong flares have an associated CME, but not all. And you can have a CME without a big flare if a region's field slowly destabilizes and erupts without a sudden flash. Now, when these storms occur, what do they do to Earth? This brings us to space weather effects. Electromagnetic radiation from a flare, X-rays, and UV arrive in 8 minutes at Earth. They ionize the upper atmosphere. This can cause radio blackouts for HF communications. GPS signals can be degraded. Essentially, a strong X-class flare can temporarily deafen our ionospheric radio wave propagation on the sunlit side. This is called an R event in NOAA space weather scales. The effect typically lasts an hour or a few hours as the ionosphere gradually recombines. Solar energetic particles. Some flares accelerate particles, mainly protons, to near relativistic speeds. These proton storms can arrive in tens of minutes to hours after the flare. These particles pose a radiation hazard. They are deflected by Earth's magnetic field for the most part, but some get funneled toward the poles, causing a shower of ionization in the atmosphere. On high-altitude polar flights, this can increase radiation dose to passengers and crews. For astronauts, especially outside the ISS, it can be dangerous without shelter. SEPs can also physically damage satellites, penetrating electronics, causing bit flips, charging surfaces leading to discharges, degrading solar panels and materials. NOAA calls these S events, scaled S1 to S5. An S3 or above can prompt airlines to reroute polar flights to lower latitudes. During one event in 2012, some airlines did this as precaution. Coronal mass ejection impact. When the CME cloud arrives a day or two later, it's the geomagnetic storm time. The CME plasma carries embedded magnetic fields. If the magnetic field in the CME is oriented southward, when it hits Earth, it couples strongly with Earth's northward field. This injects energy and plasma into our magnetosphere and triggers a geomagnetic storm. A geomagnetic storm is essentially a global disturbance in Earth's magnetic field. it causes beautiful auroras. It also can induce electric currents in long conductors on the ground, notably power lines and pipelines. In extreme cases, these currents can overload transformers in power grids, causing blackouts. The classic example, the Carrington event of 1859, caused telegraph lines to spark and even caught telegraph paper on fire. Operators got shocked. Some telegraph systems continued to operate on auroral currents alone after disconnecting batteries. If such an event struck today, studies suggest it could severely damage electric grids and satellites globally, potentially causing trillions in damages. A more recent case, March 1989, a strong CME hit Earth and caused a geomagnetic storm that collapsed Quebec's power grid within seconds. Millions lost power for hours, and some transformers were permanently damaged. In the same storm, auroras were seen as far south as Texas and Florida. Another event in Halloween 2003 caused less grid damage, but did affect satellites and caused a geomagnetic storm that disrupted parts of Sweden's grid and affected airline comms. And in 2005, a lesser-known storm still caused GPS outages for hours due to ionospheric disturbances. So, geomagnetic storms matter. They are rated by NOAA as G1 to G5 based on how much Earth's magnetic field deviates. G5 events are rare. The last truly extreme one was 2003's Halloween storm. During storms, auroras can be seen much farther from the poles than usual. People in mid-latitudes who rarely see them might get a treat. Red auroras overhead, green curtains on the horizon. It's often a surprise and delight. Historically, low-latitude auroras freaked people out. Besides auroras and power issues, geomagnetic storms can disturb navigation and create extra drag on low-orbit satellites by heating the upper atmosphere. We can often get some warning. Satellites like ACE or DSCO VR at L1 measure the solar wind about 1 million miles upstream, giving us 30,060 minutes notice of the CME's magnetic orientation and velocity before it hits Earth. That helps alert power grid operators to prepare. Spacecraft can be put in safe mode to avoid damage from high-energy particles. Astronauts can take cover in shielded parts of the ISS. Airlines can reroute flights. These mitigations rely on us detecting the sun's storms soon after they start and monitoring the in situ wind. Now, not every solar storm hits Earth. The sun is blasting things out all the time in various directions. Earth, a small target, intersects only some. Sometimes we see a huge flare in CME, but it goes off to the side. Other times, a seemingly modest flare may send a CME squarely toward us and catch us head-on. Space weather forecasters analyze coronagraph images and measure CME speeds to predict arrival times. While the largest events are rare, even moderate storms can be disruptive. For example, the Halloween storms of 2003 caused 2 large geomagnetic storms, damaged or disrupted satellites, rerouted flights, and gave spectacular auroras. That was with sunspot cycle 23 near end. It's interesting that sometimes big flares don't produce proportionally big geostorms. It depends on the CME magnetic alignment. In 2012, a monster CME shot out, but missed Earth. In 2015, a strong CME's field wasn't southward, so it produced a milder storm than expected. Beyond Earth, solar storms can affect other planets too, of course. Mars, lacking a strong global magnetosphere, gets walloped more directly. Its atmosphere gets eroded gradually by many CME hits. Jupiter's magnetic field responds with its own auroras and disturbances. Solar flares also have interesting effects. They can cause cosmic ray intensity to drop because the expanded solar wind and magnetic flux after a CME sweeps away some cosmic rays for a few days. One might wonder, could a solar flare or CME directly harm life on Earth's surface? Thanks to our atmosphere and magnetosphere, not really. Even the worst, Case solar particle storm might up the radiation slightly at ground level, but not enough to be lethal or cause immediate issues for humans. The risk is more to technology. Perhaps if a truly gigantic flare happened, you might see minor radiation effects at aircraft altitudes. But life has survived countless solar storms over billions of years. The sun's variability is modest enough that it hasn't sterilized Earth. For astronauts on Mars or future moon bases, though, these storms are a significant hazard outside of Earth's magnetic cradle. A big solar particle event can deliver a potentially lethal dose of radiation if astronauts are caught unprotected. This happened, fortunately in timing, in August 1972, a huge solar proton storm between Apollo 16 and 17 missions. Had astronauts been en route to the moon then, they could have been in serious danger. So space agencies plan to have shelters and storm forecasts for deep space missions. The interplay of flares, CMEs, and cosmic rays also extends to potentially affecting Earth's clouds or climate slightly. There's an interesting possible link. During strong solar activity, cosmic rays are reduced, and some scientists speculated that fewer cosmic rays mean fewer cloud seeds. Thus, in times of high solar activity, maybe slightly less cloud cover and a tad more warming, and vice versa. This theory is still debated. Evidence isn't very strong that cosmic ray changes make large climate differences, but it's an intriguing idea connecting solar magnetism to weather. In summary, solar storms are the climax of the sun's magnetic drama. They turn the sun from a steady light into an occasional threat. For much of history, humans noticed their side effects only as awe-inspiring auroras or disrupted telegraphs. Today, in our interconnected, electrified world, we watch the sun closely because a big storm could mean days without power or lost satellites. It's fascinating and a little unsettling that our mild-looking sun can flex such power across space. At the same time, these storms have likely been occurring for eons, and life persisted. They may have even helped Earth's atmosphere over geological time by providing energy for chemical reactions or by injecting atmospheric nitrogen oxides. On some level, they remind us the sun is not a static lamp, but a star, and all stars have tempests. The sun and Earth, a delicate balance. Despite the sun's occasional violence, it is indisputable that without it, Earth would be lifeless. The sun sits at just the right distance to make Earth a comfortable habitat. The sun sustains life in every way. It provides virtually all the energy that drives Earth's climate and ecosystems. If the sun's light stopped for even a week, Earth would plunge into deep freeze and most life would perish shortly after. Let's walk through the many threads of connection between the sun and life. Photosynthesis, the basis of the food chain. Plants, algae, and cyanobacteria capture sunlight and use its energy to turn carbon dioxide and water into sugars and oxygen. This process, which has been ongoing for 2-3 billion years, created the oxygen-rich atmosphere we breathe and feeds almost all organisms directly or indirectly. When you eat a piece of bread or fruit, you're consuming stored sunshine, the plant that made it packaged solar energy into a chemical form. Even fossil fuels are ancient sunlight. Coal, oil, and gas are the remains of plants and plankton from hundreds of millions of years ago who use sunlight to grow. Burning those fuels releases that solar energy that was stored long ago. Thus, quite literally, all life is sunlight, slowed down and transformed. A poetic but true statement. We are all made of sunshine. The calories you burn with each breath were gathered by a plant from the sun. If the sun had not shone, Earth might have some chemical energy life at deep-sea vents, but likely nothing like the thriving biosphere we know. Climate and weather. The sun's energy drives the circulation of our atmosphere and oceans. The equator gets more direct sunlight than the poles, creating temperature gradients. Warm air rises at the equator, flows toward poles, cools and sinks, setting up convection cells that produce prevailing winds and weather patterns. The rotation of Earth and the distribution of continents complicate it, but fundamentally, wind exists because the sun heats some parts of Earth more than others. The water cycle, evaporation, cloud formation, rain, rivers flowing, is powered by solar heating of the oceans and land. No sunlight, no evaporation, no rain. The sun lifts water vapor up, which then condenses and falls as precipitation, enabling terrestrial life and shaping landscapes. Day-night rhythms. The daily cycle of light and dark has imprinted itself on life's behavior and physiology. Almost all organisms have circadian rhythms, internal clocks attuned to the 24-hour cycle of light and darkness. Humans get sleepy after sunset because our pineal gland produces melatonin in the dark. Sunlight each morning resets our circadian clock, syncing our sleep-wake with the outside world. Plants orient their leaves or open their flowers with the sun. Animals might be nocturnal or diurnal, depending on how they've adapted to the presence or absence of light. Before artificial light, human activity was largely diurnal. We did things in daylight and rested at night. Even now, many of us find bright light at night disruptive and a sunny day energizing, which is a deep evolutionary wiring. Seasons. Earth's axial tilt means the sun's angle changes over the year, giving seasons. In winter, less sun and lower angle leads to cold. In summer, more sun and higher angle leads to warmth. Life evolved strategies to cope. Deciduous trees shed leaves in temperate winter to avoid frost damage when sunlight is too weak to support them. Animals hibernate or migrate to follow the sun's warmth. Crop planting cycles align with seasons. Civilizations developed calendars to predict solstices and equinoxes. These allowed planning of agriculture and festivals. Many cultures celebrated the winter solstice as a time of rebirth and hope. Indeed, our modern holidays like Christmas align with ancient solstice festivals like Saturnalia or Yule, essentially celebrations of the sun's return. Psychological impact. The sun and its light have a direct effect on mood. Winter blues, or seasonal affective disorder, is a depression that hits some people in dark winter months. It's linked to lower sunlight causing changes in brain chemistry. Treatment often includes light therapy, essentially giving people artificial sunlight to cheer up their brains. We use sunny metaphors for happiness and dark for sadness, which shows a universal intuition. Sunlight correlates with positive feelings, darkness with gloom. Physical health. Sunlight triggers the production of vitamin D in human skin, which is essential for bone health and immune function. Historically, societies in low sunlight regions had diets to compensate to avoid rickets. Conversely, too much sun can cause skin damage or cancer. So there's a balance organisms must strike between harnessing the sun and being harmed by it. Sunlight also helps regulate various bodily functions, from sleep cycles to potentially blood pressure. Moderate sun exposure tends to correlate with certain health benefits, whereas none or too much have downsides. Oceans and currents. Sun warms equatorial waters more than polar. That drives global ocean currents. These currents shape climates. The sun's uneven heating of Earth thus orchestrates even these deep ocean patterns. Extreme dependence. Virtually nothing on Earth is untouched by the sun. Even cave ecosystems that never see sunlight ultimately rely on energy that originally came from the surface. Only some rare ecosystems like deep sea vents might circumvent the sun by using Earth's internal heat and chemistry as an energy source, interestingly giving us clues how life could exist on sunless worlds like Europa's ocean or under Titan's crust. But those are exceptions. The bounty and complexity of life we know is thanks to the sun's abundant energy pouring down. Protective shields. The sun's magnetic field, via the solar wind, also helps shield the inner solar system from some cosmic rays. Earth's magnetic field, in turn, shields us from much of the solar wind. It's like layers of defense. Earth's magnetosphere and atmosphere protect life from most harmful space radiation. Without the sun's stable output and Earth's shielding, life on land would be very different or impossible. The far future. The sun won't always be so kind. In about 1 billion years, as it brightens, Earth might get too hot for comfort. That would be a slow, moving disaster, though. Later, in 5 billion years, the sun will expand to a red giant and likely end the Earth as we know it. But by then, maybe our descendants will have migrated elsewhere or adapted in ways we can't imagine. It's worth noting that while the sun's output is currently steady, even small changes have been linked to climate shifts historically. The sun might have influenced Earth's climate slightly over centuries. Now, human factors are overpowering such subtle solar changes. Beyond physics and biology, the sun influenced culture and religion profoundly, as covered earlier. Rulers aligned themselves with the sun. Ancient Egyptians had a whole theology around the sun's cycle. The Japanese emperor was believed to descend from Amaterasu, the sun goddess. The sun was a universal symbol for life, energy, and rebirth. Even today, in language, we have vestiges. Sunday, literally Sun's Day. Many national flags have suns. We celebrate things like the summer solstice in festivals. Science gave us a more factual, less mystical sun, but we still greet a sunny morning with a certain joy. So the balance is, the sun gives us life and sometimes threatens it, but mostly sustains. Earth has been lucky to have a star of just the right mass. More massive stars burn out too fast. Less massive ones might be too fickle, or have planets too close and tidally locked. Our sun is indeed a fairly ordinary star, but for us, it is extraordinary, the one and only source of light and life. Astronauts orbiting Earth often remark on the stunning view of the sun cresting our blue atmosphere, sometimes calling it a fragile layer protecting us. If you watch an orbital sunrise from the ISS, you see a bright point intensify, and then a blazing star burst over the horizon with a jewel-like thin blue line beneath, a visceral reminder of how dependent we are on that light, and on that tenuous air to moderate it for us. We live in the sun's extended atmosphere. We eat its light. We feel its warmth. We fear its storms, and we bask in its glory. That relationship has defined Earth's story from the very beginning. Life's emergence, evolution, and ultimately maybe life's end here when the sun changes state. To put it succinctly, if Earth is our mother, then the sun is our father, providing the energy of life. Both are needed, and indeed many cultures personified them that way. Even going beyond Earth, when we search for habitable exoplanets, we're basically hunting for other Earths around other suns. The conditions that make Earth habitable revolve around having a star like the sun at the right distance, plus Earth's own attributes. We basically look for similar star-planet arrangements because we recognize how fundamental the star's role is. In closing this segment, every warm breeze, every raindrop, every green leaf, every breath of oxygen, every shimmering aurora, all trace back to our sun. It's truly the heart of our existence. The Earth-Sun connection is intimate and profound. Understanding that scientifically doesn't diminish its wonder, it enhances it, as we see even more clearly how finely tuned and interwoven the system is. The sun's living past and future. We've journeyed through the sun's present workings, but the sun's story has a timeline, a biography from birth to death, with Earth riding along for part of the way. Let's step back to understand where our sun came from and where it is going, and how that shapes the broader narrative of stars and life. Birth recap. Our sun ignited about 4.6 billion years ago, likely in a cluster with siblings. We see evidence of a nearby supernova explosion around the time of the sun's birth. Certain isotopes in meteorites suggest that a supernova shockwave might have triggered the collapse of the molecular cloud that formed our solar system. So perhaps a massive star's death helped spark the sun's birth. In that cloud, not just the sun, but other stars would have formed. We find some solar sibling candidates by chemistry and motion in the galaxy, but over 4+ billion years, the cluster dispersed. As a young star, the sun was likely more active. Young suns spin faster and have more flares, strong winds. There's evidence Earth's early atmosphere experienced intense solar winds and flares. But fortunately, by the time life arose, the sun had probably calmed to a more stable state, though still a bit dimmer than today. The faint young sun paradox. Astrophysical models say the sun was 30%. The response is very long and presumably covers all points requested.